Good morning, everyone. Day 3. We went through day 1 of Frontiers, where we had Tomasz and I have a little fireside chat on the state of Ethereum, crypto, and where we're going. Yesterday, we had a pretty intense day where we had some talks focused on applications. We had an insane demo from Guillermo Adversel about the future of coding with AI and with Porto. And today, the day is a bit different. Today, the day is not focused on applications. It's focused on hardcore back-end Rust engineering. So these talks that you're going to hear about today, they're very focused on distributed systems, high performance. They're not for the faint of heart. I think they're not talks that you can lightly follow. I think you really need to lock in for these talks and pay close attention. We've done so much work to optimize our code, and we're going to start the day with Alexei and Dan from the Reth team, who will talk to us about optimizations that we did to the Reth code base since last year, which have 5x'd the performance of the node since then. And we're just getting started. So give it up for Alexei and Dan.
All right. I'm Dan. This is Alexei. We're both on the Reth team, and we're going to be talking about all of the optimizations we did about the past year since last Frontiers to 5x Reth's performance. But first, we're going to talk about why do we even need performance? Why is it important to optimize clients? Why do we spend a year doing this? So we're going to see what kind of motivates all this. One reason is growing demand, right? There are more and more people using the chain, the world's changing, and for that, we need the capacity to actually support all of these new users. The next is use cases. There are a lot of new use cases or old use cases that require high throughput, low latency, like exchanges, payments, and we need to support these use cases. If the client can't support it, then these use cases don't exist. The final thing is decentralization. If you're running a node and you have a validator, it's run on some box for a few years, the layer 1 is going to start to scale. And so you need to make sure that box can still support the growing capacity of the chain. Layer 2s are also scaling. So for example, Base has set some pretty ambitious scaling targets from 50 megagas per second to 250 megagas per second. If Reth wasn't able to handle this load, then it wouldn't be possible to actually achieve this. So we also need to make sure our L2 software is performant as well. And on the L1, because we're scaling the L1, we have set up these great end-to-end load tests and really networks that will allow us to test, is the chain going to continue succeeding when we bump the gas lot? Will it keep working when we make the state size very large? Really testing these kind of degenerate cases that might occur if you just start bumping gas limits. So these can sort of serve as a preventative measure to make sure that we see what the bottlenecks are before they actually happen in production. Next, we're going to talk about how we as a team actually try to improve the client performance. First, general principles for improving the client. There are a few optimizations we're going to talk about later today, but they've kind of taught us a few things on, like, generally what's important when you're trying to design your client architecture. And these three things are, one is pipelining. When you have a bunch of steps in a process, you only want to wait for something if it's absolutely required. You never want to wait for no reason or because it's maybe like logically simpler to see in the code. You want to make sure that you do next steps of the process if you can do them. Next thing is you need to make sure that you're actually using the whole machine, using all of the threads of your machine, using as much of your resources as possible, minimizing I/O. Not everybody has like a super fast SSD, but even if you do have a fast SSD, if you minimize I/O, everything will just happen much, much faster. Final thing is executing optimistically. These are sort of applying heuristics to make the happy path much, much faster. So if you can do something and then keep going as if some statement were true, and that statement's true like 90% of the time, and that makes your code faster, you should do that. How we actually optimize the client goes a lot deeper in terms of the tools that we use. So we have to profile a lot to make sure that the code is actually fast. It's a very, very complex piece of software, and we use this profiler called Samply to generate flame graphs. This allows you to look through like the whole pipeline of some process that you're doing or some benchmark that you're running. So you can see every single thread, you can see it over time, you can filter things. It's a really good tool for understanding what's happening in the program. And if you don't know what's happening in the client, then you don't know how to optimize it. The next is that we benchmark things. We have to benchmark a lot. We have to do this with really accurate data. If you don't have accurate data, then the optimizations you're making aren't actually going to work in the real world. So we have this tool called Reth Bench and Reth Bench Compare, which allow us to take real-world data and throw them at the node so that we can get these accurate benchmarks and see, OK, did this change that we made actually make it faster? And it also allows us to collect profiles and analyze the node very, very easily. So before we dive into the optimizations, let's show basically what happened in the past year. So last frontiers, we were about like 40, 50 megagas per second for client validation. So when you process a new block, it needs to validate it. That's kind of how we're measuring that. And you can see that today we're at like 400 megagas per second. We think we can go higher, but it's a really, really good improvement since last year. So now we're going to explain what are we actually optimizing, which process, and what changed. So the lifecycle of a block or block validation is the thing that we've been trying to optimize for the past year. And it has a few steps. So the block usually comes in, it enters the node, and we need to perform a bunch of different validations. One of the validations is the pre-execution validation. These are things like validating signatures. The next thing is the EVM. You need to actually execute all of these transactions. Next, you need to do post-transaction validations, which are calculating the state root and the receipts root and a few other things. And then finally, you need to return the response, so whether or not the block was valid. So this is the process that we are trying to optimize. And the two things that are the most heavy in the node are the state root calculation and the EVM. These are by far the most intensive things. So we're going to focus on things related to that for the rest of the talk. Last year, we had an architecture that looked kind of like this, where basically you would have these pre-execution validations, and then you have like a whole single-threaded process for EVM, for state root, for post-execution validations, and you do storage root calculation on some other threads. This is very, very serial. We took a look at this and said, OK, this is not very good. So now we're going to show you what it looks like today. And it's much, much better. We're using a lot more of the computer. So we have most of these things happen in parallel now, along with some additional things that make the node faster, like pre-warming. So from my point of view, this looks a lot better than last year. So this is where you have to lock in, as Giorgio said, because the next things we're going to talk about are the actual details of the optimizations that we did. So the first optimization I'm going to talk about is caching and pre-warming. So when you're executing a block, this will make a bunch of operations related to disk. So you'll go and fetch some data, like an account or storage slot, and it will take some time for the disk to respond with the answer. It'll do this a bunch of times throughout execution, and you have to wait for it every single time. This is very slow. We want to speed this up. So as you can see, most of the time is just waiting if you're doing kind of the naive EVM execution. So what we want to do is we want to cache stuff. We want to cache as many things as possible. And so we introduce cache. If you cache things, the disk operations can be kept around for longer, and you can retrieve them if you have them in the cache. But the problem is that if you just introduce a cache when you're executing, it's not actually going to do anything most of the time, because you're probably fetching lots of different accounts. And if you're fetching an account that's not in the cache, well, then you're kind of out of luck. So how do we actually warm up these caches to make the performance much, much better? And we do this with something called pre-warming. So that's that other box, which you didn't see from last year's architecture. So what pre-warming does is it executes every single transaction optimistically to try to warm up these caches, and then it throws away the results. So even if the transaction fails, it doesn't matter. This gave us about 30% improvement on machines with slower disks, so this was very, very nice. And here's some graphs on our latency. So when I mentioned block validation, we want lower is better. So the baseline was about 150 or so, and we brought it down to like 50-ish afterwards. So the way that it works is we have our regular execution thread. It's executing transactions. And then we spawn a whole bunch of transactions in parallel. And what this does is they will try to access most of the accounts that these sequential transactions will access, and it will load them up in the cache. These won't be perfect. It'll also load some stuff that won't be loaded during regular execution. But it turns out this is a very, very effective optimization, because most of the time it just works. Now, pass it over to Lexi.
All right. Thanks, Dan. So I will talk about two optimizations that we did in the stage root calculation part of the pipeline. First one is the sparse trie. So the main idea is that how do you calculate a stage root? You execute your transactions, you gather the state updates, you update the trie, you calculate the hashes, and then you get the root hash. What if instead you stream all updates as they happen in the trie? You keep in-memory structure that has a sparse version of the trie, so it's not the full 150 gigabytes MPT. is just the nodes that you actually updated. And you can also hash the subtries in parallel. So you can hash in parallel the storage tries. You can hash in parallel the subtries of the state root, sorry, the state trie, by basically splitting the big trie into, say, 256 smaller subtries. And this allows us also to utilize the I/O better. Generally, we get 40% improvements or even more on all machines with this change. And we had this amazing comment from a Reth BSC user who had the latency decreased from 120 milliseconds to 40 milliseconds, so 3x just from this change. This is a parallel sparse trie, so updating the subtries in parallel. And the chart looks like this. As you can see, we were at about 150 milliseconds, and it jumped to down to we were at like 200, jumped to like 100. So 2x improvement, and as you can see, there is spike here, and there are like generally spikes. This is most likely due to Zen transactions. Those who know what is Zen know that they basically spawn a lot of storage slots, and this can mess with the state root calculation. But we also fixed it recently, and this shouldn't be an issue anymore. So how did it work before the sparse trie? As Dan said, you have the EVM. It's sequential. You cannot do anything about it, but you can do some pre-warming. But then we actually execute the transactions one by one. You execute the transactions. You gather the state updates. You fetch all the trie nodes from the disk. You do some I/O, and then you fetch. And then you calculate the root in memory. With the sparse trie, what you can do is you can have two main threads. So the thread 6 here, the thread 5 is the EVM, and the thread 1 is the sparse trie. You start the execution for the transaction 1. When it finishes, you can fetch the state updates from disk. Not just the state updates, the trie nodes that were related to the state updates. So your transaction updates an account A, and it updates the storage slot for this account. What you do, you fetch a trie nodes, all the trie nodes in the path to this account in the MPT, and you also fetch all the nodes in the storage trie in the path to this storage slot. You do not wait for it to finish. So it happens on a separate thread. You just keep going with your EVM. You execute the transaction 2. Same happens to the transaction 2. You go to the disk, and you fetch it on another thread. So we try to utilize as much threads as possible. We try to maximize the I/O that we do in parallel. And when we actually get the trie nodes from the disk, we can update the in-memory trie. So as I said, this is not the full trie, not 150 gigabytes trie in memory. This is just the nodes that were in the path to the updated leaf. And basically, it takes very little memory, and you can store it in your RAM. Same happens to the transaction 2 and its updates. And as you can see, we can actually proceed to the next step of updating the hashes in a trie. So what you did, you updated the trie and the leaf values, but the hashes are still old. So the root hash is now outdated. What you do, you update the hashes of the whole trie, and in the same time, you keep executing. So the transaction 3 does the same trie node fetching, updates the trie, and that's it. That is our block. And what we do next, we calculate the root. You can notice that we can make some redundant work, because we update the hashes twice. And what if, for example, you update the same account twice in 2 different transactions, so you keep doing the same update multiple times? That's OK, because you do it in parallel, and our benchmarks show that it's actually better to do some redundant work on a separate thread than do it all without any redundant work in one thread. Next thing that's related to the state root are nibbles. So we store trie nodes keyed by a path to these nodes. And the path can be represented as a sequence of hexadecimal characters from 0 to F. Each character is 4 bits, so it's not a full byte. 1 byte is 8 bits, and a nibble is half of a byte. You need to have this data structure because a sequence of nibbles can be odd, so it's not a full byte sequence. And what we did, we basically decided to store them in a more compact way, and also use better algorithms for the comparisons, for stuff like calculating the prefixes and slices. And in the future, we can also do a very interesting thing. In LLVM, there is a native I256 type. That's obviously not native to your machine because machine is probably 64-bit. But it can do some interesting optimizations that we cannot do in Rust. But it's not possible today because of the compiler. So the compiler kind of doesn't allow us to do it yet. This gave us a 20% improvement on all machines. That was kind of surprising to me, because it's just a small change. You store, like, instead of 64 bytes, 32 bytes, and you do faster comparisons. But there is so many of them that you actually gain a 20% improvement. And it went down from like 85 to 65 milliseconds. Very good, very nice. So let's go through an example. The trie on the left, we have it in memory, and what we want to do with it is to insert a new leaf. This leaf is at the path 17813, and it has an odd length. What you do, you walk basically node by node, and you build your path. You build it all the way to the new leaf node, and then you add the leaf node in the trie. So there was no leaf node, now there is. So we have this path, and we need to store it somehow. We have a crate for it, Nibbles. Has a lot of downloads. We use it for all the trie-related things. And we store it as 5 bytes, because the high nibble is 0, and the low nibble is set. What we can do instead, we can store them as 3 bytes. So we compact the nibbles into bytes, and the low nibble of the last byte now is set to 0. We need to distinguish what is it, 3, 0, or just 3. For this, we store the length. Speeding up because we are like out of time. We have the length either 6 or 5. If it's 5, it's actually 3. If it's 6, it's 3, 0. The 3 key optimizations, if you sum it up, that we made to Reth since 2024 were starting with the bottom. So we optimize the data structures that power the execution, the stage roots, in this case, nibbles. They power the trie calculation. You optimize the EVM, you do less I/O, and you optimize the stage root calculation. So what's next? We have some ideas. Trie database is a very interesting thing. Next talk will be about it from Brian. And basically, you divide where you store your data, not just in one database, but in multiple databases. Our goal is to minimize the non-EVM overhead. So when you increase the gas limit, you should just expect longer EVM execution, but no additional like stage root overhead or I/O overhead. And another very cool thing that I'm very excited about is the block level access list. Basically, it's a path to the parallel EVM on mainnet and on L2s. If it gets in Amsterdam, we'll get it. So talk to your local core dev and get it in. That's it. Thank you very much. Questions?
Hi. In the sparse Merkle tree idea, because you are parallelizing all the trie prefetches for every transaction, how do you handle like transactions accessing same accounts? So like if, let's say, the prefetch of transaction 2 completed before the prefetch of transaction 1, then your in-memory Merkle tree is constructed wrongly. So like, how do you handle that?
Yeah, that's a good observation. Thanks. So we fetch the data in parallel, but we apply it sequentially. So there is a queue, and you apply it only in the order of transactions, because if you delete something and then you update it. It's not the same as doing it the other way around. Yeah.
Oh, there we go. First of all, awesome talk. Thanks for all your hard work, guys. One of the questions I wanted to ask was, you obviously have like a lot of parallelism going on inside Reth. Are you guys usually leaning more heavily on like shared mutable state with like mutexes and RW locks, or are you like spawning new threads that own data and like preferring the actor model for most of your parallel tasks?
Definitely second option. So we have a lot of Tokyo channels or just STD sync channels that we pass the data with. And we have standalone threads that do some work and then they pass data further. So there is no locking and it all works on just atomics. So there is minimal overhead.
How do you guys benchmark trie calculation with I/O latencies? Because right now we see the benchmark doesn't have that. Everything's loaded in memory.
Yeah, so Samply doesn't show any I/O because it's just a CPU profiler, and what you have basically like an empty space when I/O is in the progress. It's harder to measure. We basically identify on the profile these empty regions, and we see that this is just the I/O, and we try to minimize it. Usually you benchmark it via running the same blocks on main and on feature branch, and you compare if it got better in the latency. But it's harder to measure the actual I/O. For this, we, I think, have a Grafana dashboard for the system I/O, and we see how much data is read or written. Mostly read, yeah, because the written data is always the same. Does that answer the question? Oh, you mean the benchmark like
Yes.
cargo bench?
Yes, the bench.
Okay, yeah. This doesn't measure the I/O. The cargo bench is only about the latency of the trie calculation. And the cargo bench also doesn't operate on a big state. And the I/O cost comes from having a big database. So cargo bench currently doesn't have it, but Reth bench and running on a real node takes this into account.
But do you guys plan to add that to the bench? For example, you can simulate some I/O latency and then put 1 millisecond here or 2 randomly to just act like you are reading from the disk.
We welcome the PRs.
We already have that. We'll send it to you.
Yeah, but yeah, that's a valid idea. We'll think about it, yeah.
Thank you for the great talk. My question is about the parallel pre-warming phase. You mentioned that you discard the results.
Mm-hmm.
I'm wondering if there's a reason for that, or if you plan to maybe use the results of transactions that don't have any state conflicts to
Right.
just apply it.
Yes. So right now we discard the results because it was like the easiest thing to implement as like the first time. We're currently experimenting with keeping the results and doing basically conflict resolution when you get to that transaction mid-block. So the idea is if you would, you keep the results around, you keep around the state that it read, and then when you get to that transaction, you check, okay, is the state the same? So if the state is the same, nothing would have changed from the pre-warming version, and you just apply the result and keep going. You skip the execution. So yeah, it's a good idea, but we're currently experimenting with it, so yeah.
Okay, I think that's the last question. Thank you so much.
Excellent.
All right, next we're going to have Brian from Base talking about scaling Ethereum. He's on his way up now.
All right. My name is Brian. I'm on the Base chain team, and today I'm going to talk about how we're scaling the Ethereum state trie. So bottom line up front, Base built a trie database, TrieDB, This speeds up Ethereum state access from like a O of log squared n factor to an O of log n factor, amount of I/O operations for the number of trie nodes being accessed and updated. And we do this by using a trie-aware storage engine. Okay, so that was a lot of jargon. I'm going to unpack that a little bit. So the actual problem here is that our existing Ethereum nodes will store the Merkle-Patricia trie on top of like a general purpose database. I guess that was spoken out a bit in the previous talk. And this ends up causing a lot of write amplification, poor cache locality, and so forth. And last year I actually gave a talk here where we benchmarked Reth and found that like your slowest blocks tend to be the ones that update the most storage or trie nodes. So this is like a real problem for scaling the chain. So just a little refresher here. The Ethereum MPT or Merkle-Patricia trie is where all the account and storage state is stored. This is like a state tree where every branch can have 16 children, stores the hash of these children, and that walks down to your leaf nodes, which are accounts, so like balance, nonce, and so forth. Except then your accounts that are contracts can also have their own storage trie. So you have this like trie of tries. So sometimes you have like a USDC type contract that has a massive tree of its own, otherwise the leaf of another tree. So this is a pretty heavyweight data structure, but it does carry like incredibly useful attributes. It lets you succinctly prove the existence or non-existence of any state in the tree, as long as you can agree on the root hash. And this is like critical for L2s, light clients. It's like how we perform like a proof of the actual state, so you can safely withdraw your funds like back to the L1. So some of the attributes of this tree, because it has like a 16 wide branching factor, it ends up being very wide and very shallow in general. So even though your paths are like 64 nibbles per layer of the tree, you end up with like the vast majority of that branching at the very, very top. So like ostensibly, because of this branching factor, you should be able to store like most layers of the tree with only like all but the bottom two for only like 0.4% of the tree, which would let you cache the majority of the like paths for even a terabyte large tree in only like 4 gigs, which would be very easily fit in memory. But you have some like really wonky characteristics here. 32-byte catch-out caches multiplied by like 16 wide branches gets you these like pretty chunky branches that do not pack well into like I/O pages. And then realistically, like there's no way you can fit one of these branches plus 16 of its children that are max size into a single like I/O page. And again, it's a tree of trees. So when we talk about caching like all but the bottom 2 layers, that's not really well defined when suddenly you encounter another massive tree below it. So let's quickly talk about like how this works in existing EL nodes. So Geth is like the canonical, well, like the classic ETH client, uses like a log structure merge tree for storing all of its data. The good, bad, and ugly is that like writes are usually fast because you're writing into like a write-ahead log. Reads kind of depend on the age of the entry you're accessing, so it hasn't been touched in a long time. It could be very slow. And then really the ugly is that the writes are amortized and periodically compacted. So if you incur a lot of debt, suddenly your node might be completely halted as it's flushing a lot of data around and shuffling around. And then caching is also like on a per item basis. So again, like things that haven't been touched in a while tend to be much slower to access. And then like how does this work with the actual trie? So it stores these trie nodes as like a key value pair in this database. So as you access the like root of the tree and then look for its child and then look for its child and so forth, you're performing like log n searches through this tree, which each takes log n time. So that's like your squared factor. And then Reth kind of and Aragon improve upon this. So they split into multiple databases or multiple tables. So your like plain key value pairs, your accounts and storage are able to be looked up in only log time because they're stored in their own tree. But then so that helps with executing transactions quickly in the EVM. But then when you have to seal the block and compute the state root and intermediate nodes, you then have to go into this other table that has all the intermediate nodes, and you pay all the debt anyway. And there are a lot of optimizations, like was mentioned in the previous talk. But like it still has to, there's still some pretty bad worst case performance. So like in summary, you have these like great databases that unfortunately are just like a poor fit for the MPT. So like in the worst case, you might be looking at like 50 IO operations just to like update one storage slot. And the cache is just like not aware of the trie structure, so you might have like really good best case performance and very poor worst case. And because again it's a Merkle root, like you guaranteed have to update everything along the path whenever you change anything at the bottom. So we built this TrieDB. Really the novel, like the database itself is just trie structured instead of being like a log structure merge tree or a B tree. It's not really how people typically build databases, but it's relevant here for Ethereum. So it's built out of trie nodes, right? You have your account nodes, which are kind of leaves, but also sometimes they're roots of other trees. You have storage nodes, which are like true leaves at the very bottom. And then you have all your branches in between. And like branches end up pointing to children somewhere else on disk, and then also carry the hash of that child. And like we're using variable size branch factor right now so that you don't waste too much space where you have like only a couple children. And then we take all these branches or all these nodes and then we pack them into contiguous subtries and then put these on like 4 kilobyte pages. So that's like the minimum unit of I/O. If you're reading from disk or writing from disk, you're going to write one of these pages anyway. So it's good to keep neighbors of the tree on the same page, so you can ideally reduce the amount of I/O accesses as you traverse from top to bottom. So what this means is like your absolute worst case performance when you go from top to bottom is like log n I/O operations. Just the absolute worst is the number of nodes along the way. And because we have all of our MPT data, all of our hashes, you can pretty much get a proof of state for the same cost as looking up the data, just by collecting that along the way. And then like within the pages themselves, we then take like a slotted page approach. So we have these pointers that grow from one end of the page and the cells that grow from the other end of the page. And that allows us to have like durable pointers to some place on disk, even though we can resize and move around the contents like as a branch grows or shrinks. And that just like has some pretty nice properties in terms of just like accelerating the way that we are constantly like increasing and decreasing the size of the tree. Mostly for storage, I guess, where it changes the most. So there's some interesting properties. Because we have these pages that represent subtries, if you're like updating a bunch of leaves at the same time, you might find yourself branching off to multiple children that are on different pages. And that like transitively gives us like a completely non-overlapping rest of the view of the disk. So you can perform writes and hashing like truly in parallel as you branch out through the tree. And this like also opens up the door for sharded storage. If we're like a little bit less latency sensitive, we can imagine like supporting vastly larger state tries than like what you would get from like a single high performance local disk. And we use a copy on write structure, so very inspired by like LMDB or MDBX. Pages are cloned as you write to them. You have to write to everything along the path anyway, as we said from the Merkle tree. And you have to write full pages because like the constraints of the disk. So this is like a pretty low overhead solution. And what this gets you, though, is the ability to have many concurrent readers in a single writer. Readers can hold on to like a shadow fork of the entire tree, and then you only clean up those pages when there's no longer any readers that can access them. And this should be very good for parallel EVM execution, because you could have like many readers all doing concurrent reads from the same block state as you like then funnel out your state changes to like your single writer that can do hopefully like pipeline writing. And yeah, so as I mentioned earlier, we have this tree of trees. It's again pretty bad for like traditional caching approaches. So we actually like built like a custom like versioned LRU cache concept. This lets us like get pretty close to what I was saying about caching like all but the bottom couple layers of the tree. EVM has some guarantees where like you must access an account before any of its storage. So you might as well cache the skip pointer to that account every time you read it. Similarly, as you go down a couple levels of branching within either the top level or lower level trees, these are worth caching as well for a skip pointer. So ultimately, when you're actually reading any net new piece of state, like you're probably only going to do like 2 or 3 IOPS, which is like hopefully a pretty good outcome, even with like a very large tree. And kind of explain how this behavior works for this cache. Probably go back into this later. Skip forward. So we have some preliminary benchmarks. So opening up a new database, putting a bunch of accounts and storage into it, and then just like moving this file around somewhere else so that there's no IO or OS level cache. We get some pretty good single-threaded metrics here. So we can get like 400,000 account reads per second, which is like the equivalent of 1 gigagas a second. And that's just like pure IO. And account updates, we're getting like close to 100K per second, which is a similar level of gas per second. A little bit lower on the storage so far, but again, this is all single-threaded, and well, that brings us to like what we're working on right now, which is like parallel writes, parallel hashing are all kind of enabled by this sub-trie structure. So we're currently looking into how to like optimally utilize IO queues and have a thread pool under the hood, which can do all of our recursive Kejai caching and like properly saturate disk writes. And it's currently memory mapped, which depending on how much you're into databases, it's like a pretty good hack, but it's not like necessarily what you want long term. So we are like building a custom buffer pool as well, which can also intentionally pin top parts of the trie into memory. And that can get us like async IO as well with like IO U-ring. And then finally, just like doing a better job of organizing the pages. So when we need to split sub-tries versus merge them back together, just to make sure that we have like a can optimize for like either the best case or average case of how many pages you need to traverse from top to bottom. And we think this is like a pretty aligned with like the Ethereum roadmap. There's like 3 key EIPs that I think are either coming in the near future or at least being discussed. So with like delayed state root or delayed execution, we get to have this allows us to really lean into like async IO updates. This would allow us to like use like really remote storage, much more commodity hardware, and scale up the total state like to a much higher degree. And then like block access lists, which might be coming in Amsterdam early next year, will add to blocks like a list of all state that will be accessed, because we have this tree structure again, we can perform like very fast fan-out batch reads with like no redundancy. So you would be able to pipeline read all of your state in like a very, very quick fashion. And then finally, there's actually a discussion on like a unified binary tree. This is being sort of as the modern counter proposal to the vertical tree. Instead of having this 16 wide tree of trees, you end up with a single binary tree. I mean, this is just like vastly better for our use case in that you have only one tree, like consistent depth, faster hashing, and just like much easier to pack subtrees together. So yeah, like in summary, like you can check out the repo. It's open source. It's still in active development. We're working on integrating this into Reth as soon as possible. And this should decrease the amount of IOPS required. So one, just getting much faster block execution when a lot of state is accessed, but also just like not needing to rely on having like truly bleeding edge NVMe, massive NVMe local disks. Should make it much easier for anyone to run an Ethereum or base node as all of these networks continue to scale. So happy to answer any questions about this.
Thank you. So let me put it this way. So let's say we have a block access list. Now we will be able to load every storage slot that you may need before calculation. And then we have delayed execution that you can basically move the write out from the critical path. Those kind of like orthogonal optimizations, kind of like making like optimizing trial DB, the DB for the trial less important. Would you think it that way?
I mean, it definitely helps. And like right now, the disk is like definitely on the critical path for your high scale EVM chains. Getting back the extra time from delayed execution, whether that be like a 2-second or 12-second slot time, is certainly huge. There's still like it really depends on who you are in the pipeline. So if you are building blocks, then block access lists don't help you. They're only coming from the block builder. Like even if you have plenty of time to perform like the state root calculation, we still think there's like a lot of benefits to having just much less I/O dependency, far fewer IOPS, and then like the ability to shard this tree onto like many disks or like individual nodes.
Thank you.
Hi. On the question of memory mapping, have you thought of looking at a more dynamic structure where you evaluate the frequency distribution of state use and restructure the tree based on that? So the top moves, most frequently used state move to the top, which is stored in the fast disk, and the rest, sort of the longer tail, goes to the colder storage. Because the overall state is quite metastable, so this becomes very efficient on the hashing and reads as well.
Yeah, I can answer that question. So one is like we are trying to be completely compatible with Ethereum state tree. So we aren't, well, moving things around is only insofar as like how we're optimizing, I guess, the number of pages traversed or what's in the cache. But we do like we are very concerned with like worst case performance. So like the unfortunate side effect of saying let's weight our cache entirely to what's accessed typically is that then you have certain like periods of traffic where either a ton of net new storage is written or stuff that hasn't been touched in years suddenly is accessed en masse. And like this is the kind of thing that we specifically want to make sure is not like an attack vector on any chain, because we're ultimately limited by like what is the worst case performance.
I can share some testing that we've done on that front. One more question is on the sort of the frontiers stuff is on the binary, unified binary tree. This is just a comment you might have not known. Back in the day, there was a project called Handshake, which pioneered sort of this idea of having the embedded, state tree database, which they, pushed out a thing called UrkelDB, and which basically using the binary tree, and they're using Redux as well. So it's something worth looking into, and might be very interesting because, they basically had a lot of similar ideas. And I can also make some comments on that offline.
Cool. Yeah, happy to chat after this. I don't know if there was a question you want me to answer there, but. All right, I think this is our last question here.
Yeah, thanks for the great talk. Lots of details. Could you speak more about the decision to do the variable branch factor as opposed to the 16 fixed branch factor?
Oh, so because keys are typically randomly distributed because we're using the hash of addresses or hash of storage slot, you end up with a natural branching factor where towards the top of the tree you're using every single one of your children in a branch, and then as you progressively get further down, you end up with periods where there's only two children to a branch or 3 children to a branch. So right now we're using power of 2 branching just because we don't have to reshuffle the size of the nodes too much, but it generally tends to be fairly stable depending on where you are in the tree. So just reclaiming some extra space so that we have to make fewer I/O traversals along the way.
Sweet. Nice job. Yeah, come on down. Perfect. All right. Thanks, Brian. That was awesome. Next up, we're going to have Ansgar with the Ethereum Foundation talking about scaling Ethereum Layer 1.
Thanks. Can you all hear me? Awesome. Yeah, hi everyone. I'm Ansgar. I am a researcher at the Ethereum Foundation. And as of a couple months ago, I'm co-leading together with 2 colleagues of mine the Ethereum L1 scaling effort within the Ethereum Foundation. That's together with Tim Bako and Marius van der Weijden. And so I thought it would be a good opportunity today to explain a little bit how maybe this is a bit slanted towards how I personally kind of see the individual work streams on that topic and how they all basically are ideally going to fit together to help us really scale Ethereum. First thing I wanted to briefly point out is the different time scales on which this work is happening. I think there's really 3 main time scales. The first one is the type of work that a lot of the people here in the room are very familiar with, are really focused on, which is the kind of all the things that don't need changes to the Ethereum protocol, don't need hard forks. That's performance improvements in the clients, new database types, improvements to sync, all these kind of things that really make a big difference for Ethereum, but don't need a hard fork, and so can happen on shorter kind of iteration cycles. Then there's the things that do need hard forks. So that's basically the medium time scale. That's anytime you are improving the overall the scaling level. In our case, we're talking about scaling by basically changing really the rules of the system. These usually have maybe I don't know all in a 1 year kind of cycle length. And then you have the very occasional, really big kind of paradigm shifts to how Ethereum operates. So you can think the merge was one of those cases. On the scaling side, we now have a really exciting one on the horizon, which is our move to real-time ZK EVM, which will be another one of these real paradigm shifts that unlock a lot of extra scaling, but also is a multi-year project. What you should not make sure to not think of this is that you basically we're only doing this short cycle work now, and then we'll move on and only do the medium cycle, and then only do the long cycle work. Instead, basically, if you think of it as a timeline, I try to like map out the next 3 years roughly. It's really just that all of these work streams are happening in parallel. Like there are people in the EF, in the clients, in the ecosystem that work on all 3 of these different activities, and they'll basically just like it's more the iteration loops, basically like how quickly do these produce results. Is basically on a different speed. And it's a fun exercise if you try to like map out the next few hard forks. I mean, this is, don't quote me on this like in 2 years, but I actually think that I*, like the hard fork 2 after Amsterdam, is the first candidate that might already be when we bring zk-VM to mainnet. Could be like 1 or 2 later, but I really think this might already be where we have at least a shot of delivering this. For my talk, though, I will focus really on this medium timescale, because that's really, I think that where I'm mostly focused on internally. We have people, if you want to reach out to maybe Marius or Pari, that really kind of had our kind of short cycle work. And then on the zk-VM in particular, we have Kev and Justin that really kind of focus their energies on that. I will talk on the medium term because I think that's actually also quite exciting, and I really think there's a particular pattern that I'm going to try to convince you that's underlying like most of the work happening there. One more basically specific zoom in here. I'm not going to talk about all the feature work around scaling, but I want to specifically focus on just simple full nodes. So there's all different types of Ethereum nodes out there, of course, and like as we run the chain faster and faster, they'll all run into different challenges. But where the main kind of core of scaling is really just on like block verification inside of normal full nodes, right? And that also means if I say just block verification, that means I'm exclusively right now in this talk focused on what we call the burst constraints. So I think there are really 3 main resources in Ethereum, in Ethereum nodes. That's the bandwidth that you use for downloading the blocks. It's the compute for verifying the block, and then it's the disk, basically like how quickly can you basically get data from and back to disk. And so all of these basically constrain how quickly we can verify blocks as they come in. There's the entire separate kind of branch of work of how can you make sure that as the chain kind of runs for a while and accumulates load, how do you keep running it fast? Again, out of scope for this talk specifically. And then one more point that I wanted to point out, because sometimes people are a bit worried about this. None of this is about saying, well, we just run on like heavier and heavier machines, right? That's one way you can actually do scaling. And of course, I'm not saying we could never consider this in the future to at least have like some sort of one-time bump to these requirements. But all of this for now is really the idea of like, imagine we really don't want to like change anything about the requirements of running an Ethereum node. How can we just get higher throughput out of the existing considerations? And what I'm trying to convince you about is that really basically the core of this is all about just better resource utilization. What do I mean by that? There's a lot of resources on Ethereum in these Ethereum nodes, like your CPU, your bandwidth, your disk, that either sits idle for a big portion of the overall time, or at least when it is used, is not used as efficiently as it could be. And that's really like the core of how you can get more scaling out of the existing hardware. I'll just go through a few examples. A lot of this is like more high-level schematic. It's not going to be like super correct in the very details. It's more going to try to give you an intuition. Also, don't judge me for these color schemes. I'm a bit artistically challenged. But so this is basically how the Ethereum slot looks today, right? You have 12 seconds in the slot, and the first 4 seconds of that are available for block verification. I call the rest empty. Now, of course, your node isn't literally sitting empty. There's a lot of very important work happening, but in terms of just the block verification, those other 8 seconds in the slot are empty. And then in the 4 seconds, you basically have 3 main phases. One is just propagation. You receive the block. Then execution, where as you can see, it's basically interleaved. I'm trying to use these 3 different colors. So like green, yellow, interleaved, compute, and disk, because sometimes basically you execute a transaction, you hit something you want to load, you go to disk, you load from disk. Of course, hopefully, sometimes you have prefetched it, but if not, you have to basically pause execution, go to disk. So it's like interleaved compute and state access. And then at the end, there's another compute step. It's a little bit different, though, conceptually from the other compute, which is the state calculation that we also already heard about. so how can we basically just like utilize more here? I mean, one very obvious first thing is you see this empty space, right? Like we're only using a third of the slot. Well, we could change that, right? Again, we're not going to literally move immediately to a system that scales all the way to the full slot, but conceptually you can imagine there's like a 3x up to 3x first principles gain here. But just saying, look, let's try to find mechanisms to basically scale this up, use the full kind of 12 seconds or whatever. If we basically go to different slot times, use the full slot length for the verification. The two relevant features that will already like help move us towards that, or I guess yesterday we kind of decided to go with the one version of this, which is EPBS. EPBS basically, or any form of delayed execution, really like the one core focus there is basically the combination of slot restructuring and delayed execution, which basically this is really why that's exciting. That's really helping you stretch that processing to most of, not yet the full slot. That's more like the long term where we'd want to go, but like big chunk of the slot. What else can you do here? Well, in this picture, you're still doing these three things sequentially, right? You're first downloading the block, then you're executing, then you're calculating the state root. One ideal that you can try to move towards, again, you'll not immediately like be able to do that. That's actually quite hard to really like make sure that in the entire slot you can use your bandwidth and your compute and your disk in parallel throughout the full slot. But you can imagine that's the ideal way you would use these, right? You don't want your bandwidth to basically be sitting idle, quote unquote, at least from the block verification point of view, for like 2/3 of the process, and then you don't want your compute to only be useful in that portion and the disk only to be used in a small portion. You want all of this to basically run 24/7, ideally, right, in a node. How do we get there? Well, again, that's actually fully parallelizing. This is a bit trickier. There are some proposed features that already get us somewhere closer. So block level access lists, for example, are really interesting. They specifically let you parallelize more of the compute and the disk, because they pre-announce basically all the state that the block needs, so you can go start fetching this at the beginning while you already start the compute verification of the block. So that's actually quite exciting. Multidimensional metering, just a small kind of technical note there. It's actually funny. EVM is somewhat a bit complicated. If you just naively ship this, you don't actually scale the chain. Why is that? Well, because in principle, you could have a lot of compute and a lot of disk use now, because you can do them in parallel, but there's no way for users to consume both, right? Once you consume one, the block is filled, or if you want to consume both, you can only both of them are counted towards the same gas limit, so you're still basically back to the same old basket of consumption that you can do. So the nice thing with multidimensional metering, it has a similar name to the old idea of multidimensional pricing. It's much simpler though, so like no worries. It's basically just saying like, look, we keep the single one gas counter we have in Ethereum, but we basically start coloring it. So like every operation now contributes to both, like basically like you keep track of like how much of the gas that it used was for compute, how much was for disk, and then you just have individual caps. You say, look, we now maybe have twice the gas limit, but you can only spend up to half of it on compute-related operations and up to half of it on disk-related operations, and that way now you can actually make use of the extra headroom that feature gave you, right? So basically, like, again, you always have to think of not just how can you make it on paper run faster, how do you actually also expose that to the users? But again, all of these features would only be a first step in that direction. There's still a lot of like unclaimed territory that we'd afterwards have to find ways to unlock. Another example, here I wanted to first take a quick step back and talk about the work that we have been doing over the last few months, and especially like all of you EL devs have been doing a lot. Again, my visualizations today are a bit experimental. The idea here is that like the gray circle here is supposed to illustrate like the total available CPU in this case, because it's compute that you have within your like 4 seconds to verify a block, right? So basically like the distance from the center to the edges, and then these individual spikes are illustrating like how fast or slow are the different types of compute operations that you can do on Ethereum, right? So like that is different precompiles, different opcodes, other types of compute that you can use on Ethereum. And today it's actually quite annoying. Like there's a few of these really spiky operations. You can see like the one that's orange kind of highlighted here is the one that in this kind of example, that would be the binding one. You can't go any faster because this one is already at the very limit. But most of these actually have a lot of room to go. Like if you only want to do add operations in the EVM, you can fill the entire block. The entire block is still super quick to verify, right? You are not part of the problem, but still you're basically being artificially limited. So what we've been doing kind of as a loop, and again, this part of the loop does not actually require hard forks, is the clients have been running a lot of benchmarks to identify these like worst cases, and then you run this loop of, okay, you optimize, so like now the spike that used to be our problem spike got a little bit smaller. It's still not great, but at least it's no longer currently like a constraint in this picture. And then once you optimize, once you ship like an updated version of the client, you go and you scale the entire chain, right? So we started doing this. We went to 45 million on mainnet. We are preparing currently to go to 60 million, and that's exactly kind of coming from this type of iteration loop. But again, my talk is more focused on feature changes that help with scaling, and actually this is quite laborious work, right? So you actually like there's a limit to like how much smaller you can make the spikes. There's a lot of operations that are actually like very non-spiky. So the actual thing that you'd want to do with a feature is what we call like repricing, right? You just want to make sure that all of these operations cost what they are supposed to cost, so that they're all kind of the same speed. And so that's basically like in this kind of picture language, that would basically try to make this picture much less spiky so you can scale it without going over the overall constraint of the system, right? And you can immediately see that basically, like, again, it's another example of just filling more of that kind of gray empty space that otherwise is useless. Now basically you could use much more of that. And we already have one EIP that's supposed to make the opcodes cheaper that are all basically overpriced, and then we will have another EIP that will make the precompiles more expensive. And so then hopefully we are getting close to that picture. Of course, we'll not hit it on first try. Probably like even after Amsterdam, the EVM will still be somewhat spiky, but then we can basically keep iterating, keep making it smoother. If you just do this naively, so this is specific. This specific is the example of compute, right? We're also doing this now with state pricing. That's a bit earlier stages. There's a lot of really good work ongoing with BloatNet. If you heard about that, that's not just focused on this work, but it's part of their scope. And we also like starting to look into this for data. It's a bit simpler story there. If you are not careful though, what you end up doing with repricing is you end up in this picture, right? So basically, like here you would have in a way had success. You basically homogenized the pricing for all of the compute, all of the state, all of the data operations, but you didn't pay attention to their relative pricing. So basically, like data, yes, there's no particular spikiness in there, but you're still basically overpricing data in this picture. So a block that would only consume data would basically like actually still be like relatively lightweight for the system. So basically, one important aspect of repricing is that you make sure that you actually also reprice relative to each other. And again, multidimensional metering here is very helpful for once you talk about several different resources. So that's another example. There's more, right? It's this recurring theme that basically like we just have this empty space that we really want to like utilize on Ethereum. EIP 1559, right? So 1559, it's a great way that Ethereum prices its usage, right? The base fee kind of mechanism on Ethereum. It has a few flaws. One, the most relevant one for scaling is actually that in order to, the chain always basically needs a signal of how much demand is there. So it basically always says that, hey, on average, you're supposed to use half of the block, half of the gas available, so that the chain can see if actually there's more than half consumed, okay, we were underpriced, and if there's less than half consumed, we have to basically instead, we were overpriced, we have to lower the fee. This is great, this works well, but it does leave on average half of the throughput on the table, right? Like the average block, and if you run it over like 24 hours a week, a year, like half of what you could have in terms of throughput already today in today's EVM, you're just leaving on the table just so the pricing mechanism gets a signal on demand. There's basically two ways to address this. The simple one is just making this problem less bad. You basically you can claim a little bit more of that empty space by just moving the target away from this 50% mark. You could do 60, 70%. There are trade-offs, right? So basically, like the more you compress this, the more you squeeze out the kind of area where you get a signal for demand. But you really gain a lot of extra throughput, basically for free. And then in principle, that's not something we are short-term focused on. But in principle, you could like do a more involve kind of 5059 reform where you can maybe find a way to not be reliant on this kind of target underutilization at all. One more of these examples. This one actually is now zoomed more in. All of the other ones were basically like applicable to all different resources. This is an example of something that's only useful for a specific resource, in this case, compute. We've already heard about it in the other talks a bit. Basically, a parallelizing compute, right? Like your machine will have several cores, several threads. It's not, again, that they're all completely sitting idle, right? There's a lot of other things your node is doing, but it is not really being able to to reliably utilize, do multiple things in parallel for block processing. And that's maybe one thing that I didn't mention earlier. One important constraint on Ethereum, we always have to assume the worst case, right? We can't just price things for the average case, and it's, in particular with things like transaction parallelization. There's a lot of really good work on optimistic parallelization, where you just hope that you can run them in parallel, that you can prefetch the state that they use, and then most of the time you're actually successful. But if someone basically tries to screw with you, they could create a block that makes you fall back to sequential processing. And so we always have to run the EVM at the speed that would still allow you to run safely at that lower throughput load. The idea here would be to really make sure that you can guarantee parallelization. The feature that helps there a lot is block level access list. It actually helps in two ways. Because it has the state diffs for the transaction, it allows you to run multiple transactions in parallel. Here, of course, the idealized version of you only have, I don't know, you want to run on 3 threads and you have 3 transactions. They're all equally long. You can run them perfectly parallel now. And another underappreciated aspect of block level access list is you can also run the entire state root computation. That used to be this extra section at the very end after you process the block. You can now run that in parallel as well, because you already know when you receive the block what the state diff will be. And you can, for example, actually one thing that I think we should explore more is you could start focusing on your compute on that while you actually go to disk to load all the data you need to then do the execution. So it's actually, that part is also really exciting. And again, it's just the otherwise empty cores that you didn't use are again, just extra resources that are available that we can't reliably use yet on Ethereum that we would unlock here. As I said earlier, it's not all just examples of take resources that otherwise just sit empty. There's also some examples of a resource is already used at its maximum, but you just use it smarter. And I just wanted to briefly, I didn't find good ways of illustrating this with silly graphics, so it's just text. But basically, because we saw a compute-specific improvement already, there's actually one bandwidth and one state-specific improvement, which is kind of nice. So we can make headway on all these fronts that come more from this direction of just efficiency improvement. So on bandwidth, that is what I just call amplification reduction. So right now, on the CL side, where the block propagation happens, we're using gossip sub, and that has this amplification factor of roughly 8. So basically, every message you send on average 8 times, you receive 8 times. That's basically wasting, quote unquote, your bandwidth. How can you basically just still use the same amount of bandwidth, but basically deduplicate without losing the propagation speed? There's some ideas there. They are not as advanced yet as some of the others, but basically there's the proposal for gossip sub v2, which would basically just announce messages. You pull them, you can deduplicate that way at the cost of a little bit more latency. There's also ideas of using erasure coding, so that basically you just send small chunks of the messages in the network, and then you can just assemble the message once you have enough chunks. Disk, the last example here basically is the example here that I wanted to bring in terms of more efficient usage is state load batching, right? So today, again, in the worst case at least, if you process a block, you just run the block, it does an S load, you stop, you go to disk, you get one value, you come back, you keep executing, it does another S load, you go get one value, you come back. With block level access lists, you know all the values, so you can go and much more efficiently just batch read the values from disk. So that should be another speed up there. And then the last thing I wanted to mention here is that actually, of course, very different time scale, as we talked about earlier, but the ZK EVM work is, in a way, the ultimate example of just using existing resources more efficiently. People always focus on compute, because ZK, basically, at the very core, is a compute compression mechanism. But it's actually all 3 resources. That's the beauty of it, that it helps use more efficiently. It moves all the data, all the block data, into DA, into blobs. So whatever multiplier you get in terms of you only have to sample the blobs, you don't have to fully download them. You get that all of a sudden now also for Ethereum mainnet throughput. So there's a big multiplier there. On compute, of course, you only have to verify the proof. And then on disk, you can now run stateless enabled by the ZK. So actually, you basically it really is like a huge efficiency gain there as well. So you can really think of zkEVM as like this example of like a huge just like improvement specifically on just efficiency of resource usage. A few caveats. Basically, if we zoom out here, as I said earlier, right? First, this was all just focused on full nodes and just block verification. There's many other operations, many other things we have to like keep in mind, where we have to make sure the performance is still good as we scale. So it's not as easy as just claiming that free real estate. An example that I think is especially kind of like illustrative here is RPC nodes, right? RPC nodes that basically like actually really kind of need to do very heavy other tasks as well. And in particular, zkEVM is, I think, something where we have to like start preparing well in advance. zkEVM is amazing for lightweight nodes that only want to follow the chain, but if you actually want to have some of that data, if you want to have some of the data, you still need to download it, and so on, right? So basically, like in zk, basically, it really only have some node types, and we have to make sure that the other nodes still are performant as well. And then, as I said, all of this is only focused on in the moment. The chain becomes heavier and heavier over time as it grows. So what do we do about state growth? We already have some solutions that we're working on for history growth. You maybe saw that we recently dropped pre-merge history. And then also things like sync. There's many more of these. So it's not all just as simple as the picture I presented. But I really think at the very core of scaling is this loop of basically just making block verification faster. One last thing there. Also, as you basically get pushed closer and closer to the limits of what resources a node has, you are reducing your margin for error. So for example, there's now a work stream as well on like a CL side hardening of the chain, so that basically because as the chain fractures, you have to like keep like rolling back and forward blocks and whatnot. And if you're already at the very limit of how fast you can go, like it's really starting to create problems. So that's another caveat. But really, if there's like two takeaways from this talk, I would say one is the timescales, right? Like we have these 3 different timescales on which we do scaling work, and they're all ongoing in parallel, both in the EVM and in the EF and outside. And then also the other big takeaway I think is really that on this like feature side approach to scaling, most of the unlocks really come from resource utilization. So you should really kind of think about kind of Ethereum scaling mostly through the lens of making better use of the available resources. And that's all. I think I have a little bit of time for Q&A. Thank you. And again, sorry for these graphics. It was a bit experimental.
Hi, Ansgar. Awesome talk. Thank you. I had 2 questions for you. The first is about the timelines you were sharing. You were sharing how the first one is super fast because these clients can do it on their own, and then the third one is super long because they're very hard, like cryptography problems. About the middle one, I think one thing that's kind of understated is the amount of consensus that's required for these 3 changes. The first one, like, there's not a lot of consensus required. It's usually a centralized company or foundation. For the third one, there's a lot of consensus required. And for the second one, there's a lot of consensus required as well. Yeah. Can you talk about how that impacts the timeline of the second one? Like, do you think it's feasible that protocol changes can happen on a predictable timeline because of like the factor of consensus? And then the second question is related to your slide on the bandwidth, and this one. Oh, yeah.
Sorry, yeah, I'll go back to that.
Okay, the second one is on the next slide about the bandwidth, compute, and like scaling efforts. Given that you guys are trying to work within the constraint of like hardware, like we want Ethereum nodes to be able to run on like you shouldn't need to be like a company to run these nodes. Like people should be able to run these nodes at home. Given that Ethereum developers still have not come to consensus on what the minimum bandwidth and hardware requirements should be for a node, like how does that make these scaling efforts, like how does that impact how you guys know like by how much to improve scaling and the trade-offs when like you don't have a clear like agreement on like what the node requirements should be, especially as you like diversify like the type of nodes too.
Yeah, good questions. So
Thank you.
the first one on the timescales, indeed, the top row here is a bit special because you can just do it. You don't have to like ask anyone for permission, which is great for iteration speed. I do think in the more recent past there have been a few examples on kind of Ethereum governance where I think we were a little too unfocused in a sense. Like it was just not clear like for what reason should we prioritize features. I personally think that's more a temporary side effect of the fact that Ethereum didn't really like have a clear kind of direction to go in. Basically, it was a lot of like one-off features that were just like nice to haves. I think as we are now kind of moving more into a kind of time again where we have like clear main priorities, scale the L1, scale the blobs, and improve UX and interop, I think that will actually help make most changes less contentious. I think basically in a sense, kind of like now the discussion around the Glamsterdam features is like the last time where we basically did not yet come out of a time period of already preparing with a specific theme in mind. My prediction, maybe a bit naive, would be that the hard forks after will be significantly more streamlined. Of course, timelines are always hard, not just in terms of the governance side of it, just the implementation overhead. So like here I assumed 8 months between different hard forks. Some people are trying to aim for 6. Some are more like thinking it's going to be 9. I don't know, I was trying to be somewhere in the middle. There's always some uncertainty around this. I personally think we are hopefully improving there. The other question in terms of no agreed hardware specs, there is, actually, there's this EIP 7870, which we basically like accepted on all codevs as like some sort of meta EIP where we said, okay, look, these are the specifications that you need to have so that we can guarantee you actually can keep up with Ethereum mainnet. Back when we decided that, there was more like a theoretical thing, so people like there was not super much attention. I think now as this becomes more load-bearing, as we scale and really push towards these limits, we will probably revisit those. Some of these might actually go a little bit down, some might go a little bit up. But I do think we will, there's no way around it. We will basically have to have some sort of reference spec for the minimum Ethereum machine, and I think we are already kind of basically there with that EIP. Awesome. I think I don't have time for more questions, so I'll be around for the rest of the day. Just come find me. It's an exciting topic. Let's scale Ethereum. Thank you.
That was so good. All right. Thanks so much, Ansgar. That was amazing. Next up, Roman is going to be from Ithaca talking about Ethereum acceleration with Reth.
All right. I see there are a little bit less people in the room today, so I'll need your hands for a little while. First of all, a lot less people are interested in the underlying technologies that make consumer apps possible. So I want all of you to give a round of applause for yourselves because you're building the protocols and technologies that power the consumer apps. And secondly, I want again to thank Ansgar for his presentation and the amount of all of the work and effort that EF Research and Ansgar specifically puts into making Ethereum as efficient and as scalable, and the blockchain of the future is just insane. So another round of applause for Ansgar. So my talk will be split in 2 parts. In the first part, whereas Ansgar talked about the medium-term changes to Ethereum, I want to talk to you about Ethereum Endgame and how efficient and performant Ethereum could look like, where you could build a business enterprise-grade apps. And the second part, I want to bring you all back a little bit to the values that brought us into this industry in the first place. And one of these values is privacy, and how we can bring back privacy to Ethereum. So without further ado, I will need a little bit more of your time, and we'll do a little show of hands. First of all, how many people run Ethereum nodes? How many people use those nodes for RPCs? how many people run Ethereum validators? Now, another a little bit more intricate question is, didn't you find it weird that there was a block every 12 seconds, a copy of the block is received by each one of your nodes, and each one of your nodes has to re-execute the block all over again? Sounds like this is the task that could be made more efficient. And over the past year, a lot of people have been developing zero-knowledge technologies that allows for cheap verification and allow to alleviate this burden from Ethereum nodes. And once you receive the block and you receive the proof for the block, you could just cheaply say that, yes, this block is valid, this block is the new chain head, and I'm going to continue building on top of it. So the future of Ethereum is ZK, and let's talk about how we can get there. So first of all, what does ZK unlock for Ethereum? ZK gives us a way to scale the L1. So it gives us cheap block verification. It gives us interoperability, because once you have a ZK-proven block, you can make small proofs about the transfers or deposits that you have made in this block, and then use it on the destination chain to be able to bridge your assets. And then it gives us privacy. And specifically, it allows you to hide certain part of information about yourself when you're interacting with the blockchain. Now, we have talked about what ZK unlocks for Ethereum, but now let's talk about how to get there. So first of all, and Ansgar touched on this point a little bit already, is we need to restructure the slot. Currently, we do not use efficiently all of the 12 seconds that we have in the slot, and there are a couple more improvements that we can do there. Secondly, we have this term called prover killers. And the prover killers are the expensive opcodes and precompiles that make proven time much higher than it needs to be. And I want to say that some of the gas prices on Ethereum that we have today, they're a legacy of unknown reasoning behind the decisions of how the gas prices were assigned. So now seems like a great time to reevaluate what does each operation actually cost relative to the block processing time. And the third prerequisite are performant provers. As you might have seen, there have been more than 20 different teams working on performant ZK VMs to prove L1 blocks. So now let's look a little bit closer into how to tackle these problems that stop us from making L1 ZK. So first of all is inefficient use of the slot time. Here you can see the current slot architecture. And basically at T0, you have the proposal time where the proposer takes its block, and it can start broadcasting it to the network. And at T0 plus 4 seconds, you have the attestation deadline. What attestation deadline means is that every validator has to receive the proposed block, and it must have validated it by the attestation deadline. As you might have seen in a couple of previous talks, the block processing latency can be as high as 100 milliseconds, and broadcasting it to a large number of validators in the entire world can take as much as well. So it sounds like we could make this more efficient. All right, these are not all of the slides that I have, but that's OK. Now, the slot structure with a proposed EPBS proposal is that instead of broadcasting in that short 4-second window, we start broadcasting the block at the attestation deadline, and we have all the time until this mysterious abbreviation PTC, but you actually don't need to care about it. Consider it just as a broadcast deadline. So you now get a distinct time in which you can broadcast large payloads. Now, the validation can happen all of the time from the moment that you receive the block to the next attestation deadline. So it gives us a way to use the slot more efficiently. Now, I want to take you back to the previous slide for a second. If you were to prove the block, you have to do it once you receive and validate it. Now, essentially, the current slot structure does not give us any room to prove the block. So you might have seen developments from SP1 and how they worked on proving the real-time blocks, proving blocks in real time. What it actually means is they state that they can prove the block in 12 seconds. But this is not enough for the testers to actually make use of the proofs, because you want the proof to be available at the attestation deadline already. So now in a PBS, your entire proving time, you have the proving time from the broadcast deadline to the next attestation deadline. And the main difference with the PBS is that it actually gives us allocated time to give room for the provers to prove the block. Now, there is another proposal, which is delayed execution, which actually gives you similar properties, where you have time to prove the block from the attestation deadline to the next proposal slot. So the attesters at the next slot can make use of these proofs and cheaply validate the blocks. So this might be a little bit difficult, but one statement that we get all of this is we get allocated time for the provers to use to be able to prove the block so that they can broadcast these proofs to the network, so the network participants can then cheaply verify the blocks. Now, the next boss of getting to ZK-L1 are these mispriced opcodes and precompiles. And there is a lot of great work being done on actually identifying these inefficiencies within the EVM and assigning the proper cost to each one that also accounts for the proving complexity of these operations. And the third boss is actually having the performant provers. And here you can see the list of all of the teams working on different ZK-VM implementations that will make ZK-L1 possible. Now, I hope that you guys will get as excited about this Ethereum long-term future as I am, because when we get ZK-L1, we will be able to get rid of all of the inefficiencies in the network that we have today. Now, the second part of my presentation is how we can actually make use of the wonderful ZK technology that we already have today on the app layer. So how does L1 privacy look like once we start integrating ZK VMs into our nodes? So first of all, I want to get you acquainted with a concept or one of the proposed solutions of how to hide your identity. So supposedly, an identity is just a random hash or a unique ID that represents you on the network. Now, the way that you can create this random hash is you can derive it from your public key and make a certain salt just to make the identity, just to avoid other entities from mapping your identity back to your public key. Now, where you can use this identity is on the RPC level of the node. You can create specialized endpoints, which I will show you in a second, where you can pass the message that you signed over and the public key. And these specialized RPC methods would be able to prove that this identity actually belongs to the address behind it without actually revealing the address. So what can we do, or what kind of use cases can we implement on the RPC level to make this possible? Now, we could think of something like a proof namespace, which exposes all of these aforementioned methods. And the first use case would be proof token balance. Let's say I want to go to a lender, and I want to tell the lender that I have a certain amount of collateral of the token that I want to borrow against. But I don't want to reveal the address that owns these tokens. How I can achieve that is I can achieve that by creating a proof token balance RPC method that takes as an input the aforementioned message and signature needed to derive the identity, a block hash of the block at which I'm trying to prove that I own the certain amount of tokens, the state root of this block against which I will be proving, and the actual account proof of the account that owns the balance. Now, the only public inputs to this program are the block hash, or the public outputs of this program are the block hash, because the verifier will need to verify against which block the token balance was proven. The derived identity, because this is a unique ID that the verifier will be using to verify that I have an X token balance, and the actual balance that we are verifying. Now, we can take this method a notch further, and we could say that I don't even want to reveal my token balance. I just want to prove to the lender that I have a certain minimal required of the token balances, the certain minimal required amount of the tokens to qualify for this loan. So the only things that this ZK program commits is the block hash, again, to be able to verify against which block this program proved the token balance and the identity. And the min balance is one of the inputs that ZK program would have to commit to as well. Now, a different use case is proving that your identity has never interacted with a certain X address. The way you could do that is you could build up a ZK program that would prove an execution trace of the transaction. Once you prove the execution trace transaction, you could also assert a statement that this execution trace never accessed the account in question. And the use cases for which this is useful is for something like audits, or proving that your source funds never came from a hack or illicit sources. And again, all of this can be accomplished without actually revealing the source, the original address that you are trying to prove. And if we generalize this endpoint even further, we could prove different assertions about the state itself. Let's say I own a maker vault, and I want to go and get it insured, and I want to tell the insurance company that this maker vault has never been liquidated, but I don't want to tell them which one of the maker vaults it is. So the way to do it is I would take a bunch of storage proofs for the slots representing the amount of time, the number of time that the vault has been liquidated. I will assert that this amount of time is 0, and I will broadcast the proof, or I'll send the proof to the insurer, so they would be able to raise my insurance score and give me a better insurance rate. And on the other side, what the verifiers would need is the verify RPC namespace, where they could verify all of these different assertions that the original users wants to prove to them. So I went on a little bit of a tangent, and I thought of how Ethereum privacy pipeline would look like in the future. So first, you have the isolated environment. This is your laptop or your PC where you do have access to your private key. And this is where you generate the either identity proof or identity signature that then you would go to the next step, and you would invoke one of these proof namespace endpoints, either on the prover or on the prover network, that will give you the proof about the assertions that you're trying to make. And then you take this proof, and you go to insurers, you go to the lenders, you go to auditors, and you're able to make different assertions about different state or your funds that without revealing your original identity or the address about which you're making the assertions. I think this is the end of the presentation. The main point that I want to deliver, that the second part of the presentation, all of the proof namespaces, all of the verified namespaces, they're accomplishable today. You can utilize Reth SDK. You can plug in the ZK VM of your choice, which has a usable SDK like RISC-0, like SP1, and you can already expose all of these methods on your node today. Thank you for listening to me. Any questions?
So for the RPC of proof no interaction,
yep.
Are all the users' address like shielded? I mean, like, because if everyone else's address is shielded, including the hackers, then how can I generate a proof that I never engaged with just an identity proof that moved the fund?
So not all of the addresses are shielded within the execution trace. What the assertion that you're making with prove no interaction endpoint is that there is some address in the execution trace that the user has a private key to, and it has not interacted with another address in question that the verifier is trying to avoid interacting with.
Got it. So it's so address is not shielded, in short, right? So only the proof shield the user's address, right? When you verify the proof, you cannot know my address, but still for this ZKL1, everyone is still storing their funds under plain text address, right?
Yeah, so you're making assertions about Ethereum state as it is represented today.
Got it, thank you.
The only thing that you are shielding is the subject in question, the address that you're trying to make assertions about.
Hi, so
Hi.
How do you see like proof namespaces and ZK EVM like affecting the hardware requirements of like different nodes? And like I know that like SP1 has prover networks and stuff, but if we're plug and playing ZK VMs, then are some like going to end up requiring that nodes like have their own dedicated GPU provers, or will we end up in a world of like delegated proving in order to keep hardware requirements low for our nodes?
The way I would answer this question is it is always about the trust model that you are trying to build. So you would want to run a self-hosted node capable of processing these methods if you never want to reveal your identity to the prover network. But if you feel comfortable with a bunch of random processors to generate the proofs for you, you're comfortable revealing that identity to the prover network, then you can utilize that as well. more concretely answering your question about the node requirements, if you want to run a self-hosted node capable of generating proofs, yes, I think you would have to have a dedicated GPU cluster.
Okay, thank you.
Thank you for your talk. If I understand correctly, the first few slides, eventually the provers are going to become baked in the network, and then you're going to have to reprise some of the opcodes.
Yeah.
Related to one of the earlier talks, which was basically mentioning that you'll have to basically cut the gas price into different segments for like compute data and so on and so forth. Are you thinking of another sort of like gas type segment for ZK specific operations? Because like ZK compute is not the same as normal compute. And also it depends on what kind of ZK VM you're using specifically for the compute.
Yep, I agree. The thing is that when we get to ZK L1 and we try to generate the proofs for entire L1 blocks, we would have to prove the entire block, meaning that its normal compute, its normal data would all be proven within the ZK L1. So we're not talking about ZK-specific operations in the VM yet. We're talking about having all of the normal operations that we have today, just being able to generate proofs against them, or proofs of them. And then, yeah, the table that was shown here is which operations that exist today are difficult to prove relative to the amount of gas that they consume.
Okay. Yeah, I guess my question was like, for instance, in a ZK VM, it's much more expensive to do like a store operation than like in real compute life. And like the way you execute the store operations actually influence the cost inside the ZK VM.
No, so actually executing a store operation is cheap. What is expensive within ZK VM is any kind of cryptography, because there are a large number of mathematical operations that you have to prove.
Okay, thank you.
All right, thank you.
Good job, dude. All right, thanks, Roman. That was awesome. Next up, we have Rosowski and Danny talking about Foundry.
Thank you. Thanks, man. Hello, everyone. So the title of this presentation is Foundry, and apparently it wasn't updated, but our main point here is that we want to secure $1 trillion on-chain with Foundry. Right now, we're not super far away. We are not like probably a few hundred billion, but for the next trillion and for the next 10 years, we're looking to use Foundry to secure the next $1 trillion on-chain. So we still see a lot of this kind of like hacks where protocols lose hundreds of thousands of dollars, millions of dollars of their users' money in what could have been a simple test written in Foundry in, as you can see here, like 30 seconds. In this specific case where like a condition for a only owner check was inverted by accident, and this wasn't caught by manual review, by presumably security audits of the contract, because it's such a simple mistake that is easily missable, but it's very simple to make a test case for. So we still see these kinds of hacks even today. What we're trying to aim for with Foundry is to make the experience for both the developers and the security auditors very simple and easy to catch these kinds of things by providing excellent tools, fast, efficient tools. As Georgios mentioned yesterday, the goal of Foundry is very similar to the Rust compiler's goal of empowering developers to build efficient and reliable software. So in our case, empowering developers and smart contract auditors to build efficient and reliable smart contracts. So another thing is that developers end up delegating a lot of their security measures to almost entirely to the auditors, but the auditors don't have all the time in the world. They have an allocated time slot where they try to find, well, they would like to focus on critical things such as the core logic of the protocol, but end up just a lot of time wasting time just finding these very simple and easily catchable mistakes in their code in the smart contracts that could have been easily caught with just very simple tests. And so in this screenshot, you can see that the auditors explicitly said that because we found so many bugs in this audit, it's statistically likely that there are so many more that we just either didn't have the time to or the resources to find them ourselves. So, so this is our goal with Foundry. We last presented at Frontiers 2024, where we had 400 contributors. Now we have 500. We're always growing in PRs, in contributors, in stars. Foundry is, I believe, in the last Solidity survey, was the biggest test framework that people use, with hundreds of respondents saying that they use Foundry over Hard Hat or other frameworks. So another thing we're going to highlight here is that we released 1.0, so we're committing to stable releases, and this is our release process right now. We still have our nightlies that are built every day off of the main branch, but now we have stable releases that we branch off of master every month or so. Right now, we begin with an RC. So we create a release candidate that we ask people to test using the RC version. Then we iterate over the RCs, and we eventually release a new version. And then if any bugs or regressions were found after the release, we make a patch version. So the main highlight here is that we have RCs. These might not be super easily findable, but we do ask people to test using these versions. It helps us out for feedback on new features and performance improvements, for example. Something else we do in this release process is that we now have also attestations with the releases, so Foundry app will automatically verify that the releases are correct, and alongside the hash, we also have like attestations on GitHub releases. As part of the release process, we also run benchmarks. We consider performance regressions as any other bug, so we do block releases on performance regressions. And in general, we try to have performance improvements on every release. So now we have benchmarking as part of the release process, benchmarking against previous versions. So here's the timeline since last year. We released Solar, the first version of our Solidity compiler. We released Foundry 1.0, Alloy 1.0, a bunch of Foundry versions, which we'll be talking about soon. Last main highlight is that we now have a new website. It was rewritten using Vox, which is the static documentation generator written and maintained by the WAGMI maintainers. We also have migrated the Alloy and the Reth website using this new framework and a new style for our websites. So we released Solar last year in November. What is Solar? Solar is our Solidity compiler written from scratch, inspired by the Rust compiler. So the main focus of Solar is improving the developer experience of Solidity developers. As many of you know, the main bottleneck at this point in the Foundry development cycle is actually just building the project instead of just running the tests. Usually tests run faster than a clean build of the project. Or even just a recompilation of the project, because, and this is mainly due to the Solidity compiler being pretty much slow. Nothing else to say there. So our main focus here is just trying to, the only path forward we saw to improve this is because Solidity compiler is kind of like a black box. We just pass it in the sources, and then we get the output back. We decided to write our own compiler from scratch with performance in mind, with modularity in mind, with extensibility in mind. So our, let's see. This is one of the benchmarks. As you can see here, Solar with thinking is way faster than Sol-C. So, OK, never mind, like, wrong one. This is the actual benchmark. So the main part that's currently done, like Solar is still work in progress, but we do have a part of a front end, and this includes the parser. So the parser is currently 5 times faster than Sol-C on average. And the ABI is 50 times, up to 50 times faster. For example, here on Solidity, it's 1.5 seconds versus 30 milliseconds. So we use this extensively in Foundry to analyze the project, to traverse the AST for various things, including like the new Forgelin, which Mark will talk about. And here's another benchmark, or OK, what else? So currently the front end is almost done. We have the compilation pipeline done up to the ABI, which is essentially just emitting the interface of your contracts. So we don't have bytecode generation, which will be our next focus, including these are some other focuses, like, for example, the middle end IR. We want to have like a generic abstracted intermediate representation for us to be able to support multiple backends. For example, the new Solex released by the newly released Solex compiler, which is currently just a backend, and others, for example, Venom from Viper, or even Yule. So we released Foundry 1.0. This is a few of the highlights. This is benchmarked against Foundry 0.2, which is, I think, 2 years old at this point. But obviously, we have way faster compilation, way faster tests. We added a bunch of new cheat codes, including gas snapshots, which are extensively used by a lot of people to measure the performance of the smart contracts. We have new cheat codes for symbolic execution. So, for example, you can integrate it with control. We often release support for the new hard forks way ahead of time so that people can test it. And of course, we're committing to stability and reliability for the future. In 1.1, the main thing we wanted to highlight here is that we have added support for a new configuration flag called dynamic test linking. This is also to address like the main bottleneck of compiling Solidity, where we what this does is essentially decouple sources from tests, so that when you modify a source file, the next time you recompile, you don't have to recompile the entire project. And this saves up to, this is up to 130 times faster, as you can see here from the benchmarks. In one case, from 130 seconds to 1 second. So, yeah, thank you. Some highlights are just improved performance, UX improvements, and new Anvil endpoint. It's simulated v1. It's actually extensively used in Portal. So if you're using Portal and you're using Anvil to locally, you now have support for each simulate v1. So you can use it locally. Another thing is we released is Alloy 1.0. Same thing as Foundry. We commit to like supporting and like stability and reliability for newer releases. Alloy is just a rewrite of EtherSRS from the ground up, re-architectured. The website is also migrated to Vox. These are a few benchmarks against EtherSRS: 50% faster U256, for example, and 10x faster ABI encoding thanks to the Sol macro. These are a few of the highlights. Don't have much time to go over. The main highlight here is that the Sol macro lets you write Solidity inline in your Rust project. And this also enables you to have way faster ABI encoding, decoding, and a nice high-level wrapper for the smart contract so you can use it to call functions on chain or simulate whatever. Last thing, I'm going to pass it to Mark for 1.2.
Yeah, so we have a lot of stuff to unpack. Maybe the time for Q&A will be a little bit shorter, but yeah, let's get into it. So Foundry B1.2 was like basically like an ecosystem integration release. We integrated the new Etherscan v2 API, where they unified all the endpoints, and now you have a single API key. We are still backwards compatible, but they will be deprecating like B1 soon, so we will do the same as well. Then, as Danny mentioned, like we already had early EIP 7702 support, but it was more of a like prototyping sort of support. So here we did like further releases, and we added new features, right? So that now we would have like a dedicated Anvil endpoint. We also added support in CAS, so that you could like assign and recover like auths, as well as like attach auth lists. And then we had to patch an issue that we had in Forge where nonce like management wasn't properly handled. Now you can also like set empty code again if you delegate to the zero address. And we also support like cross-chain delegation as well as like multiple delegations, because before we were limited to just one. So all this stuff, like the community kept opening like issues, and we kept like progressively iterating. Yeah, so in Foundry B1.3, it was like this was a big release. It went live like not too long ago. This was like one of the biggest like security-focused release that we had, and I think it really sets like the tone for what's coming, right? So yeah, despite its like highly like feature focused, as always, we focus on performance. So this is built on top of REVM 27. We also dedicated like some effort to improve the stack inspector, and this like ended up giving us like more or less 20% improvement when running like Forge tests, which is pretty cool. On top of that, Matt had an idea, which is that for fork tests, when we need to get the account information before, or I mean, it's still the case, you need like 3 RPC calls. So he created a new endpoint on Reth that allows us to get all that information with a single API call. So when you are doing fork tests, if you use a Reth node, you get like up to 11% of like time savings in your test, which is pretty cool with just like this new API endpoint. So we encourage like other clients to also integrate this endpoint because it's pretty cool, as you can see in the benchmarks. Yeah, so as per the features, one of the highlights or like one of the biggest things of this release is Forgelin. So basically, with Forgelin, we bring static analysis capabilities into Foundry, which is like super powerful. For those of you who don't know what static analysis is, it's that basically, thanks to Solr, we analyze the code, right, and we get an idea of its like semantic and capabilities, right, of the code that you've written. And then based on that, we can like identify patterns. And based on those patterns, we can flag you issues that your code has. So this is not, this doesn't require any runtime. So even before you've written any test, like you've just like write your Solidity code, we can already tell you, hey, you most likely have a bug here, or you could do this better in this way. So this is super powerful. And now we just need to keep adding links to make it better. More on this like in the following slides. We also gave a lot of effort into improving like testing, especially invariant testing. So now we will have like coverage-guided fuzzing and time-based campaigns, as well as stable testing. I'll explain it in a couple of slides. And then other cool features that we have, highly requested by the community, especially auditors, is like better support for EIP 712 signatures and hashes. Like apparently, a lot of devs were doing mistakes when generating the hashes or when encoding their structs. So we added new cheat codes and neat commands that make it super easy. You can then verify that your code is sound. And as everything that we are doing, we are always trying to document everything. We have high standards for that. So you will find like example in the docs, and you can simply copy what we do and adapt it into your code bases. We added new Anvil endpoints, so similar to how in Foundry you are used to, like in Forge, you are used to deal balances in your unit tests or like fork tests. Now you can do the same in Anvil with some MPI endpoints. So you can deal ERC20s or deal ETH approvals. And we also have support for querying blobs and sending raw transactions. And finally, this is also pretty cool. Now Foundry has like a log file, so you can pin dependencies. So yeah, for example, if you have like some OpenZeppelin dependencies, you may have a food gun if you don't pin the dependencies because they push a lot of stuff to their main. So yeah, this is pretty cool. Gives us a lot of like peace of mind, and it's something that the EF wants to push into all the development frameworks. So pretty nice. Yeah, so for Forgelin, I'll like explain a little bit more what it is other than like these static analysis capabilities. Our idea when we designed it is that it's highly inspired in the Clippy experience that we get in Rust. So it's like an enhancer of your like productivity and like the security of your code. So it leverages Solr's AST and HIR, and especially like its visitor traits. And with that, we can identify the issues, as I mentioned. And then we also use Solr's like diagnostic emitter to emit like these warnings. It's really easy extensible. So we build it in a way where you simply write a macro. Like you define your struct, you write a macro. All the boilerplate is handled by us on the background with this macro. And then you only need to implement either the early lint pass, if it's an AST-based lint, or the late lint pass. So anyone can come. You write the macro, and with the implementation of this trait is where you really focus on the security logic. You assess whether you should issue the warning or not, and that's pretty much it. From a user perspective, how it looks is that you can configure which source of lint you want. Like we have different severities. You can decide which like files you want to be linted, which not. So it's pretty flexible. What else? Yeah. So we also issue code suggestions. And basically, when when you see the lints, you will see how to fix them. And by default, it runs on build. So I will speed up because we are over time. There's sorry, we will be a little bit late, but I will try to unroll. So basically, we have some cool PRs that you can easily create lints with Cloud Code, so please check that out. We will help you. Here's some examples. Pretty cool that it's not only security-based, so we can also help you if you face something like code size limits, right? You may not know it as a developer, but you can use some tricks like reducing your modifiers, and this is a lot of stuff that we can flag. This one is coming soon as well, so we will have gas savings. You will be able to have your small vectorized optimizer, and we will prompt you to do some inline assembly to improve stuff and make it more efficient. Then for invariant testing, basically we implemented this coverage guided fuzzing. For those who don't know what invariant tests are, is that basically we chain a lot of calls across your contract with different patterns and also with different call data, and we hope to break the invariants that you defined. So coverage-guided fuzzing is a smart way to do that. We maintain a corpus, which basically is the state of each of these calls, and then based on the calls that look promising or the sequence of calls that look promising, we can find new paths and hopefully unfold a path that breaks the invariance. We support different strategies, and we can add more in the future. Time-based campaigns means that you are not limited anymore by the amount of rounds. Now you can say, I want this invariant to run for, I don't know, 2 days. So you leave it running in your server, and then you can come back and see the findings, which is pretty cool. And you have a nice progress bar indicator. We also added table testing, which basically is something the community requested. The idea is you define a test case, input and output. With a forge fixture, you can define all the different test cases of the table, and then you write test, the name of the fixture, in this case sum, and you simply assert it. We have examples in the docs. So yeah, wrapping up, I have just a couple of slides left. What's next? So we explained a lot of stuff, but we are we are going to unpack everything that we have. So for what's next, super important, the solar rollout. So as you've seen, every time that there's a sun means that this was powered by solar, and there's a lot more stuff that it unlocks. For example, we are working on a faster formatter. We will have more powerful lints. So eventually, with solar, as we keep improving it, we will have a control flow graph, and this will allow us, for example, to detect reentrancy, which is not possible yet with Forgelin, but it will be down the line. So the idea is that thanks to solar and thanks to stuff like Forgelin, we will be able to raise the floor of security that devs offer. Right now, or until now, Foundry has been a lot about raising the ceiling, where we offer all these invariant testing fuzzers. But if people don't use it, we cannot benefit from that. Thanks to these features, we bring the security to the devs, and that's pretty cool. There's also an open PR to implement an LSP. This is also possible thanks to Solar. Pretty cool. We will probably help there. There's one PR which is close to being ready, which is mutation testing. It's been done by these guys, the Wonderland. Pretty cool. Also, before I forgot to say it, but it was in the slides. Shout out to Alpha Raj, who's been the guy carrying all the invariant testing. That's super cool, and he's been helping a lot. Same here. We love community contributions. And basically, what mutation testing is that you may write tests, but with the fact that you pass a test doesn't mean that your test is safe, right? So with mutation testing, what we do is we flip the conditions. For example, if you have minus or minus or equal than something, we will mutate this, convert it into just a minus, and then we can rerun the test and see which tests survive and identify weak spots on your code, tests that need hardening and stuff like that. So it's pretty cool to find edge cases that otherwise would be missed. And yeah, we will continue improving the fuzzer. So everything that I explained is just for invariant tests. We are bringing this also to the regular fuzz test. We will remove the prop test dependency, which right now makes us execute everything single-threaded, and we will basically run it in parallel. So your test will run way faster. We will also have the ability to drop tests once we find a failing test. Because right now, because of prop test, we need to wait until the execution finishes. But with a flag, we will be able to drop tests early, which is pretty cool. And finally, we will have an AST-seeded dictionary, which means that rather than starting with an empty dictionary and not knowing anything, basically, we will be able to pull in values that we think are interesting that can allow us to find breaking test cases beforehand. Then we have also the Anvil integration for Reth. So I don't know if people know it, but Anvil is a standalone node. And this means that there's a lot of development effort by our engineers in maintaining Anvil, right? This doesn't make much sense because we have a team, an excellent team who's doing Reth. They built a great SDK. And yeah, the idea is to do the work just once and benefit from that. So once we integrate Anvil with Reth, we will have production performance sort of for free locally. We will have all the extensibility and composability. And the main benefit is custom precompiles, which is something that people really, really ask. And last but not least, we also want to solve multi-chain pain points. We are aware of that. We are working on those. And basically, we need to improve the verification workflow. We know it's tedious to run it for all the block explorers. We know that it's tedious to run it for all the chains. And also, we know that devs right now are doing trickery with FFI and JSON files to import variables on their setups for multi-chain scripts. So basically, we will work, or we started to work already in improving all of that, which is pretty cool, and should help you have safer deployments, which in the end is what we all want. So yeah, that's it for the talk. I just want to say thanks to all the contributors. Foundry wouldn't be here without all of that. We encourage people a lot, please, to use the release candidates. This will help us not move things to stable until they are safe. And any contribution is welcome, even if it's docs, PRs for feature requests, for issues. Anything that you can do is super welcome, and we encourage you to do it. So I don't know if we have time for QA, but we can try it. Thanks, guys.
Thank you.
Sounds good.
Right.
All right.
Awesome. Nice. Awesome. Thanks, guys. OK, next up, we have Storm from Paradigm talking about sovereign data singularity.
Last talk before lunch. So in the world of data, we talk a lot about scalability. We want to scale up the size of our data sets, and we want to scale up the speed for collecting and querying those data sets. But today, I want to talk about a different type of scalability. The thing that I want to scale up is myself. And in particular, I want to scale up my personal capacity for collecting and managing and consuming new data sets into my workflow. And this is a challenge that I run into very frequently as a researcher at Paradigm. And so today, I want to talk to you about Absorb, which is the new tool that I've been working on to solve this problem. So this is our data reality in 2025. A few years ago, life was pretty simple. You could just run a single archive node and get most of your data from that. But these days, crypto data has exploded in complexity. We have tons of chains, tons of data aggregators, tons of platforms, data services, and off-chain data is becoming more and more relevant. In TradFi, we have stocks, commodities, we have different economic indicators that are becoming more and more relevant. This graphic is showing just some of the data sources that I've had to use over the past year. And you're going to need a lot of these if you want to maintain a good understanding of what's happening on chain. But since every one of these sources has a different API, different constraints, different schemas, different edge cases, the bottleneck for consuming these is often not the speed or the size of my hardware. The bottleneck is my own ability to juggle and manage these data sets. So what does it look like to actually use these data sources? In the past, I've talked a lot about collecting data, but data collection is just one of the many steps in the data lifecycle. So you have to find the data, you have to collect it, store it, validate it, keep track of where you stored it, you have to keep it updated over time, and then you also have to query it. And these tasks aren't that bad if you just need to do them every once in a while, for a single data set. But the problem is when you need to manage multiple data sets from multiple data sources. The time and the cognitive load of these tasks really starts to add up. And it can become very tedious and error-prone because there's a lot of repeated work and lots of edge cases to handle. So this is why I built Absorb. Absorb is a unified toolkit for managing all of your data sets. It can collect your data, validate your data, store your data, query your data. Absorb was designed by asking, what are all the common patterns for performing these tasks? And let's build a standardized tool that can cover all those patterns. And as of this morning, Absorb is an open source project, and we just put out a preview release on GitHub. So how does Absorb work? Absorb is composed of 3 pillars. First, there is a data catalog that contains millions of data sets from more than 20 different data sources. Absorb can collect any data from this catalog. The second pillar is a toolkit for performing all of those different data management tasks that I described a couple slides ago. And Absorb can perform almost every one of these tasks with a simple CLI command or a simple Python function call. And then the final pillar is a query engine that is super efficient and has super polished UX. Each of these pillars is somewhat simple in theory, but what's special is that they're all co-designed to work really well together. And a big goal is developing synergy between these pillars to create sort of the ultimate system for juggling and managing a large number of data sets with minimal cognitive overhead. So going one layer deeper into the architecture, here's a flowchart. Everything starts with the data catalog that defines the available data sets. And you can use the pre-made data sets, or you can also define your own custom data sets. Then Absorb has a command line interface and a Python interface that can be used to collect the data in that catalog and also manage it. And these can be collected directly to your local disk, or they can be collected to cloud buckets. And instead of using a database, each data set is stored as a series of Parquet files. This has a ton of advantages for making the system more simple and robust and efficient. And in case you haven't heard of it, Parquet is a common file format for storing tables of data. And it's basically a much better version of CSV, where the data is natively compressed, but it's also queryable, and you can do partial reads of it extremely efficiently. So Absorb provides a really powerful interface for querying these Parquet files from Python. But alternatively, these files can also be ingested by tons of different tools in the data ecosystem because Parquet is a common open standard. So let's talk about the data catalog. Absorb can pull data from almost any source that is relevant to crypto. This includes any table or query on Dune or Allium. This includes data aggregators like DeFi Llama and CoinGecko. This includes any raw data set collected by Cryo. And this includes TradFi data sets, like data from the Federal Reserve or various stock exchanges. Absorb takes the API from each of these sources and transforms them into simple flat tables. And by making these sources accessible in a single interface, Absorb scales up your personal ability to consume data. So the next thing to talk about is Absorb's data management capabilities. And to demonstrate these, let's imagine that we want to analyze stablecoins. We want to compare the total supply of stablecoins to the total US money supply, along with some other economic indicators. So let's walk through each step of the data lifecycle with Absorb. So we'll start off with the command line interface, which you can access by typing ABS in the terminal. And it has a bunch of subcommands. We'll cover a few of those subcommands. So the very first thing we can do is type ABS ls. And that will print out some of the data sets that are available in the catalog. And it can display this in a few different ways, but by default, it's just showing one line per data source, along with some of the tables from that data source. And from this list, we are going to use the Fred M2 dataset. M2 is one of the most common measures of the US money supply. And this data is sourced from Fred, which is the Federal Reserve's economic database. Fred tracks more than 800,000 economic metrics, and Absorb can collect all of them. So if we go to the Fred website, they have this graph of M2 over time. And you can see that we're currently around $22 trillion for the United States money supply. And in our analysis, we basically just want the data in this graph. But we don't want to be burdened by things like figuring out the horrible Fred API, or remembering where we stored the data, or keeping the data set updated over time. We just want the data. So instead, let's go back to the command line interface, and let's learn a little bit about the Fred M2 dataset. We just type ABS info fred.m2, and that tells us a few different things. So we get some metadata, we get the URL to the web page I just showed you, and it also shows us a schema that shows the structure of the data. You can see that it has 4 columns, timestamp, raw value, value, and metric, along with the data type for each column. And then at the very bottom, it tells us that this is not a data set that we have collected yet. But if we had collected it, it would tell us things like the size on disk, the number of rows, and the last time that it was updated. So I think we're ready to collect the data. We do this by just typing ABS collect and the name of the data set. And for a lot of these data sets, they aren't very big. It takes longer to type out the command than it will to collect the actual data. And this just reiterates that oftentimes the challenge is not scaling our systems to handle massive data sets. The challenge is scaling up ourselves to consume these data sets more efficiently. So the collect command, it has a bunch of different features. For example, if you run the command multiple times, it will see, oh, the data's already been collected. I don't need to collect it again. Or, oh, since the last time I collected the data, there's only been a small update. So I'll just collect the small update. And you can also manually specify any time range or block range that you care about. So let's take a peek at the data that we just collected. We can do this by typing ABS preview and the name of the data set. And this shows us what the first few rows look like. You can see that there are 4 columns, as expected. And we can see that the total US money supply was only $286 billion back in 1959. And we can generate these previews extremely quickly thanks to Parquet. Even if the data set is hundreds of gigabytes in size, these previews take less than 100 milliseconds. Again, a lot faster than it takes to even type out the command. So the collect command gave us a copy of the data set stored locally on disk. But maybe we want to store our data sets in a cloud bucket. Absorb makes this really simple. All you have to do is ABS upload fred.m2. And this can be useful if you're trying to share your data across multiple machines, or maybe you want to use cloud database services like Athena or Snowflake or BigQuery, or maybe you want to share the data with some collaborators or the general public. And then conversely, you can also download the data sets with a single command. You just type ABS download fred.m2. Now, like a lot of data management tasks, uploading and downloading to cloud buckets is not very complicated. However, when you have to perform lots of other tasks for lots of other data sets, all that time and cognitive overhead really starts to add up. So Absorb streamlines all that and gives you a simple, unified interface for all your data sets. Now, to actually query the data, let's switch over to the Python interface. The Python interface has all of the functionality of the CLI, except Python is more programmable, especially if you want to perform complex transformations on the data. So to query our data set, we type import absorb, and we pass the name of the data set to the query function. And this loads the data into a polars data frame. And if you aren't familiar with polars, you should really check it out. It's basically a Rust-based replacement for pandas that is way faster, way more robust, way more memory efficient, and has a way better UX for queries and transformations. And under the hood, Absorb uses polars for many different operations. The query function uses lazy loading, partial reads, and a bunch of other tricks to make these execute extremely efficiently. So let's imagine that your data set is hundreds of gigabytes across thousands of Parquet files. Executing a query might require only touching a small number of those files, or maybe a small bit of each file. Absorb and polars together are able to take advantage of this, and in many cases, you can run queries faster on your laptop than you would get from BigQuery or Dune or Snowflake. All of the different operations that we performed for the Fred M2 dataset also work for the other datasets in the catalog. So here we're going to query 2 additional datasets, the Allium stablecoin supply data and data on foreign holdings of US treasuries. And a nice feature of the query function is that if the datasets have not been collected yet, the queries will still work. So before executing the query, Absorb will collect the data, save it, and then any future queries to that data will be super quick. Another nice feature is that most datasets in the catalog are normalized with similar schemas, which makes it easy to join tables across different sources, as is being shown here. And the last task that I want to talk about is creating new datasets. Absorb makes this process really simple. You basically just say, this is the metadata, this is the schema, and here's how to collect one chunk of the dataset. Absorb will use all this to collect the chunks, validate that they're correct, and keep the dataset updated over time. And the data can be sourced from anywhere you want, including web APIs, including other absorbed data sets. So for example, you can use this to convert a bunch of REST API endpoints into a series of nice flat tables. And there are a lot of options that I'm not showing here, but they basically give enough flexibility to cover all of the weird edge cases that appear throughout the data catalog. So that's a mini overview of how to use Absorb. I think it'd be helpful now to compare Absorb to some of the more traditional crypto data tools. The first category of data tool is data platforms, like Dune or Allium or BigQuery. These are paid platforms. They have lots of curated crypto data sets. They run queries using SQL. And they also abstract away a lot of the infrastructure management tasks. And for some users, these platforms are a great option. But they also have lots of limitations. So first of all, there isn't any single platform that has all the data. A lot of the most useful data sets have licensing issues. So for example, the API data from Binance or Kalshi or GitHub is never going to reach these platforms. Second, unlike Absorb, none of these platforms have first-class Python support. Instead, they use SQL. And Python is significantly more expressive than SQL. It's also more modular and maintainable. And it also has a large ecosystem of data libraries that don't exist in SQL. Additionally, when you are working in Jupyter or other notebook environments, Python has a much better UX than SQL. The next reason is that sovereign architectures like Absorb can be much more cost-efficient and hardware efficient than hosted platforms. And this isn't true of every situation, but modern query engines like Polars and DuckDB and others can be very efficient, even when you're processing hundreds of gigabytes of data. And there are tons of queries that run faster on my laptop with this architecture than you would get on a hosted platform. And then there are also lots of situations where it's important for you to be able to reproduce or control the data yourself. So it's not always well documented how these platforms created the data sets. And sometimes you want to check their work, or you want to control the pipeline to avoid things like rate limiting or vendor lock-in or discontinuation. Another question you might ask is, why should I use Absorb when I can just build my own data pipelines with existing tools like Dagster and dbt? These are great tools, but they have a different focus. Absorb is purpose-built for crypto data workflows. It's not trying to be a general orchestration tool like Dagster, and it handles more stages of the data lifecycle than dbt. And unlike these tools, Absorb has a large data catalog that is tightly integrated into a query engine and a management toolkit. This leads to a better Python UX as well. So with Absorb, you're getting a lot of things that you can't get from other tools. And I see Absorb as a natural evolution of data workflows in crypto. In this world where there are so many different necessary data sources, Absorb gives you access to the largest catalog of data. And if you're using Python or the command line, Absorb will also give you the best UX for interacting with that data. But most of all, the big unlock here is a simple unified interface for data management. If running a data management task takes you only 2 seconds instead of 2 minutes or 20 minutes, this fundamentally changes your relationship to the data. Not only will you spend less time doing data plumbing, you'll end up exploring and consuming more data because so much of the friction is gone. So that's everything I wanted to say. We just put out the first public preview this morning. It's simple to install with this UV command. And try it out. I'd love to hear if you have ideas for how to make it better. So thanks, everybody, for your attention.
Let's do 2 questions, and then off to lunch.
First off, thank you so much. Like, I can't believe how many pain points you just solved. But I was wondering, one thing that did seem missing from your presentation is how do you handle auth for all of this stuff? Like, what happens if you try to query a data set and you don't have an API key set up? Or
Yeah.
how do you see what API keys you're missing for your data catalog?
Yeah, so the way that Absorb handles this is that when you're creating a data set, you specify the auth that you need, whether it be like environmental variables that hold API keys, or you need to validate that some library is installed. Absorb has metadata fields that track all these things. And if you try to collect the data set without those things being set up, it will tell you exactly what's wrong and prompt you to be like, hey, fix it. We need a key for this. Like, go get the key.
Yeah, thanks a lot, Storm. I'm curious if there's any magic or anything special you're doing on the connector side. Like, you have CoinGecko up there, you have L2B, which is like not supposed to, well, they say there's no warranty. Like, how do you handle the brittleness of some of these APIs?
Yeah, I mean, this is like part of the entire sort of problem statement here, is that there is so much brittleness and diversity and constraints, and these things aren't static necessarily over time. But there are tricks you can do. So like CoinGecko, for example, if you don't have an API key, you basically just need to heavily rate limit things, and that ends up working. L2B, their API is like, yeah, it doesn't come with guarantees, but it just reflects what is the current schema for that API. And presumably, these are things that you can set up the proper tests to make sure, like, oh, well, this is breaking now. Let's update the schema as needed. And there's also a versioning system built in where it'll tell you if the schema is outdated from a different version.
Thank you, Storm. One-hour lunch break, and then we have Eric and Osiris to talk to us about priority block space for humans and P2P flash blocks.
things for you.
Good afternoon. I hope lunch was great. We had an awesome morning session, and now we're going to get into the afternoon session. I'm going to start with Eric and Osiris from World, where they're going to talk to us about priority block space for humans and peer-to-peer flash block propagation. Give it up for them.
What is it? All right, guys. Yeah, thanks so much for coming in to listen to our talk. We're super happy to be here at Frontiers. My name's Eric, or you might see me around on GitHub as Forerunner, and this is my buddy Cyrus.
Yep, and we're going to talk about priority block space for humans and P2P flashbox propagation today. Cool. So we're going to start with priority block space for humans. The goal of this talk is to give you guys an understanding of the mechanics and how it works. So this is a flashbot, or this is a quote from DMARS from Flashbots. Where bots create congestion, PBH is a highway for humans. And this is how we see it. PBH is a fast lane for World ID users on World Chain. So why PBH? Like, what is the rationale behind PBH? We analyzed over 700,000 blocks on World Chain, and bots used 20% of gas but paid less than 0.4% of fees. And bots and automated systems regularly consume over 50% of the block, and this is a general OP stack trend. We see automated systems spamming priority fees to try to target one specific point in the block, and it crams block space, and everyday users have to pay higher fees and see longer latency as a result. So enter PBH. PBH, at its most fundamental level, introduces a new ordering mechanism into the block builder. So we split block space into two categories with the primitive of World ID, where one subset of the block space at the top of the block is for verified World ID users, and the other subset of the block is for non-verified users. And within each subset of the block, we order with the canonical max fee ordering policy. So the PBH stack is composed of World ID is the basic primitive. Rundler, built by Alchemy, is a custom implementation of a 4337 bundler that we use. The PBH 4337 contracts, obviously World Chain is built on the OP stack, and our block builder is built on top of the Reth SDK. And I didn't mention it in this slide, but we also integrate rollup boost, which allows us to have an external block builder within the OP stack. So World ID is a primitive that we built at WorldCoin. It is a set gated by the entry point being the orb. It's a Sybil-resistant set, and our semaphore circuits allow any user that's within the set to anonymously prove their inclusion in the set. And it allows a user to generate a Groth16 proof on device without sharing any secrets that they can use to prove on-chain or off-chain to any verifier that they're a part of the World ID set. There's two important public inputs to the circuits. One is the signal and the external nullifier. These are chosen by the verifier. And it's usually some external context related to the action ID that I'm verifying the proof against. But in the case of PBH, we use the signal as a commitment to the user operation. So it's the user op hash. And the external nullifier is a commitment to the date and a monotonic nonce increment that is equivalent to the amount of PBH user operations sent within a time frame of a month. Cool. So rollup boost, this is a very oversimplified diagram, but this is the basic flow. all consensus messages from OP node flow through rollup boost, and then we split those messages between OP-geth and our block builder. So OP node is going to tell rollup boost to build a block. Rollup boost will multiplex that fork choice update to OP-geth in the block builder. OP node will ask for the block, and then that get payload will be multiplexed again between the builder and OP-geth. Rollup boost then validates the payload of the builder through OP-geth with a new payload call prior to feeding it back to OP node. So this is a redundant system. And if it fails validation or times out or otherwise, we'll always have OP-geth is like the canonical block builder to fall back on. But in the happy path, every payload from the builder is used. Cool. So this is the basic flow diagram of the 4337 contract architecture, at least from from user operation to bundler through the contracts. And so we introduced 3 new contracts to the canonical 4337 stack: the PBH signature aggregator, the PBH entry point, and a custom 4337 module attached to our users' smart accounts. And so the basic flow here is user crafts a user operation. They overload the signature field with an encoded payload that has both the world ID proof and some peripheral metadata like the signal and the external nullifier. They send that off to the bundler. The bundler will then validate the user op through the smart account. The 4337 module will determine if it's a PBH user operation or not, and if it is, it will return the authorizer as the PBH signature aggregator. And the bundler uses the signature aggregator as a grouping operator in the mempool. So all PBH user operations will be grouped together. And this is just how bundling works with all aggregators. So there's a really nice primitive to bootstrap off of. So we get PBH user operations grouped together. From this point, the bundler will call handle aggregated ops, and it will overload the aggregated signature field with actually every payload encoded within every user operation's signature. And then the PBH entry point will verify all signatures. After that point, it will proxy the call into the normal entry point contract for 4337. The one other niche thing here is the entry point will call out to the PBH signature aggregator to validate the signatures, at which point it will call back into the PBH entry point and verify that the hashed ops that it sees are the same as the hashed ops that the PBH entry point saw. And what this does is it creates a cryptographic link between the signature aggregator and the PBH entry point, such that the bundler has no control over whether the PBH user operations go to the entry point or the PBH entry point. It has to go to the PBH entry point to not revert. So the bundler cannot turn a PBH user operation into a regular user operation if they wanted to. And so block production within the world chain builder really boils down to 3 main components. The Reth SDK made this super simple to build. It comes down to world chain ordering, which implements the PBH ordering invariants, the world chain transaction validator, verifying the semaphore proofs, and the world chain payload builder actually executing the transactions. And the rest of the node is just bootstrapped off of Reth. And so here's a code block, just a simple code block of how we actually implemented the ordering within the world chain builder. As you can see, super simple. We just added a isPBH field bool to our own priority, which is the world chain priority. And this determines the order of transactions that are coming out of the transaction pool. And then as you can see, we just check if a PBH payload is attached to the pooled transaction type. And if it is, we set it to true. And that's really all we needed to do to override the ordering invariance from Reth. Here's another code block. This is the PBH transaction validator. And it's very simple. Its only job is to check the target on the transaction. If the target on the transaction is not the PBH entry point, it just goes through the OP transaction validator. Otherwise, we validate PBH. And at this point, we'll attach the PBH payload, the PBH payload to the pooled transaction type after decomposing the call data, and then we'll verify all semaphore proofs attached to the bundle. And if it fails that, then if it fails transaction validation, there'll be a custom RPC. Will be realized by the client with a custom RPC error. And the payload builder, also super simple. Basically, block space is split already into two categories just through the ordering mechanism. Validation is just basically validating that nullifier hashes associated with the proofs. There's no duplicate nullifier hashes within a single bundle, which wouldn't be caught by the contract. And then execution just comes down to executing verified transactions up to the PBH gas limit, which is a proportion of the block gas limit, and then executing non-verified transactions up to the block gas limit.
All right, incredible. So I'm going to change gears a little bit, and we are going to talk about peer-to-peer flash blocks propagation on world chain. So just to give you a really quick primer of what flash blocks are, and I'm sure most of you already know, unless you've been hiding under an OP stack-shaped rock. But flash blocks are basically taking a big OP stack block, chopping it up into equal chunks by time, and then we propagate those blocks out to the network, and then nodes can consume them, and then use them to serve more up-to-date state to people who are requesting it. Why is this cool? Why do we want flash blocks? I think there's like one really obvious answer, and that's UX. So basically, when you submit a transaction on world chain, you can, instead of waiting 2 seconds, wait about 200 milliseconds. So we're thinking about an order of magnitude improvement in UX for your transaction to land on chain, and you can see your little green check mark pop up on your DeFi app. Another one is more frequent MEV auctions. So rather than having one big MEV auction at the end of a big block boundary, we can instead have a lot of small ones. So instead, we'll have 10 for each block. Why is this good? This will make more frequent, but also smaller arbitrage opportunities. And smaller ARB opportunities, we don't know for sure, but we hypothesize we're going to have more efficient markets because of this. And then another one, which I'm going to touch on at the end of this presentation, is higher throughput, but I'll leave that hanging there for now. So I want to talk to you about the peer-to-peer propagation layer. But before I do that, let me talk about how flash blocks are propagated right now. And the basic idea is rollup boost, which Osiris was explaining how that works before, sends a fork just updated with payload attributes to the block builder. The block builder says, oh, sweet, OK, I'll start making blocks, and also send those flash blocks back to rollup boost. Rollup boost sort of now acts as like a middleman, and then forwards those flash blocks over to a WebSocket proxy, which then fans that out to the rest of the network as a whole. This works, obviously, but we think we can do just a little bit better. So we have this architecture diagram that Osiris showed earlier, but this time there's a little bit more to it. You can see now this is depicting a high availability framework. So rather than having one builder, one sequencer, we've actually got N of them for better uptime guarantees. And you can see there is no communication from world chain back to rollup boost for flash blocks specifically, and those are now propagated over the existing RLPX peering framework directly from the builders over to anyone who wants them. So let's talk about some of the things we want to maintain with peer-to-peer propagation of flash blocks. So we want per payload, per builder authorization. So we want to be able to change which builder is building per block So how we do this is essentially rollup boost, when it sends a fork choice updated with payload attributes, also attaches an authorization. And all that authorization is essentially the rollup boost signature over the builder's public key and payload ID, so that it can basically have authorization, and other members of the peering network can trust that, yeah, this builder actually does have authorization for this payload to publish these flash blocks. All P2P messages, as it currently stands right now, are authorized. And this is really useful because it means that like random people can't come join the peer-to-peer network and start spamming transactions. We'll know because they're unauthorized, and you can ban them as a peer. And we also want to maintain the same trust assumptions that rollup boost currently has. So right now we want to maintain that rollup boost is in fact the decider of who gets to publish flash blocks and when they get to do it. So the obvious question and sort of a hard problem to deal with is we've got a busy kitchen, we've got an HA framework, and we have multiple builders who could all attempting to be published at the same time. So some of you may know that with OPStack HA, there's an entity called OP-Conductor, and that manages which sequencer is actually active, and thereby which builder is also active. But during a failover situation, you can have basically where we're switching from sequencer 0 to 1, and therefore builder from 0 to 1. But there is a one block area where we could have two builders potentially thinking they're building at the exact same time. This is obviously really bad because the whole core premise of flash blocks is when we publish them, we're guaranteeing, hey, this is a real flash block, it will land on chain, and we really don't want to break that promise to users. So if we've got two builders also publishing at the same time, that obviously violates that. The solution is really simple, and we can just publish start and stop signals along this P2P network. So basically how it works is a sequencer failover happens, a new builder starts building, but they're going to go, hey, I want to start building. They publish that to the network. The current builder will receive that and go, oh, OK, I'll stop. And they publish that stop signal to the network. And then when the new builder receives that, they can go ahead. And I know a few of you are already thinking, that sounds way too simple. That can't possibly work. But it can, because we actually have Raft consensus operating in the background on OP-Conductor. So if there is some sort of race condition in this peering layer, we can actually just wait one block for Raft to figure everything out and then proceed from there. So we can keep it nice and simple. And the peer-to-peer network is obviously aware of, there might be bad actors on this network. There might be people who are potentially trying to censor flash blocks or do something else nefarious. So we have a reputation system where we basically dish out reputation penalties for people that submit bad messages, messages that we've already seen. Maybe they're trying to replay messages back to us. We can just dock the reputation, and eventually we'll ban them. And now I'm going to touch on the thing I mentioned earlier, which is how do we increase throughput on WorldChain or for anyone else who is consuming flash blocks. And this is with incremental execution. So this has been touched a few times already in the talks today. But this actually basically bumps that up and takes it to the next level. Because now instead of incrementally computing the state root as we're executing transactions, we're actually getting the block before it's published, or parts of the block. We're getting the flash blocks before the real block is actually there. So as we receive flash blocks, we can execute those transactions. We can incrementally update our state root. And optimistically, we're doing this. And then at the end, when we receive the total block, all we have to do is verify, oh, yeah, these flash blocks were real, validate that the transactions actually did land on chain in the order we assumed, and we're good to go. We're already done. State root computation over. Yeah, that's kind of all I wanted to share with you guys on peer-to-peer flash blocks. We've been working pretty hard on this over the last month. This is the team over at Tools for Humanity, which is the development entity for WorldCoin. And yeah, we got a lot of cool Rust engineers. We're doing cool stuff all the time. Yeah, we're always hiring. So if there are any Rust engineers in the crowd that are looking for to work on cool projects like us, then yeah, feel free to reach out. We've got tons of partners that are here, especially big shout out to Flashbots, who this wouldn't be possible without, and with Paradigm. Everything that we're doing here is built on Reth. So I mean, obviously, none of this would be possible without all of the awesome devs in this room. And yeah, I think that's time for questions. So if anyone's got any burning questions, hopefully we've got some good answers for you. Thank you. Cool. All right. Sounds good. All right. Thank you, guys. Appreciate it.
All right. Thanks for that. That was amazing. And next up, we're going to have John here with Succinct. He's going to be talking about real-time proving Ethereum with SP1 and ETH. Reth.
Okay, can you guys hear me okay? Okay, it's working. Great. Yeah, hey everyone, I'm John. I'm one of the co-founders of Succinct. We work a lot on making zero-knowledge proofs really easy for developers to use. And one of the biggest initiatives that we've been focusing on in the past year or so is real-time proving. I'll go more into detail about why real-time proving is so interesting, but it has a lot of really great implications for Ethereum and the roadmap, so I'm super excited to deep dive into it. So to start off, what is real-time proving? I'm not sure everyone in this crowd has heard this term or even knows what it means, so I wanted to spend some time defining what it actually is. So the TLDR is that it's the ability to generate a zero-knowledge proof of executing any arbitrary Ethereum block in under 12 seconds. Now, the reason why generating zero-knowledge proofs of this computation is interesting is because zero-knowledge proofs have this magical property, which is that no matter how complex the computation you're proving is, the verifier actually only takes constant time. So in practice, right, you can imagine that you have some computation. It takes tens of seconds or minutes on your laptop. If you're able to generate a zero-knowledge proof of that, the verifier just takes this proof, it just runs some code, and within tens to hundreds of milliseconds, it can verify that this computation had some output. So in the context of Ethereum, this technology has actually already been used. There's a lot of these things called ZK rollups, which use this property to settle batches of transactions on L1. But real-time proving is really interesting in the context of the L1. So let me go a bit deeper into that. So today, with Ethereum L1, we kind of have this block building pipeline. We have this situation where block builders bid to submit blocks to a proposer. Proposers send blocks to validators, who then execute that block. Then these validators basically check, hey, did the proposer submit like a valid block? They vote on it. And one key thing in this entire pipeline is that there are like these physical bottlenecks to the system, which, and one of these biggest bottlenecks is like actually the amount of time it takes to execute these transactions. And this kind of upper bounds the potential TPS of Ethereum. So with Ethereum in particular, the community and when Ethereum was started, it had these certain values, mainly around decentralization. So one of the key things that the Ethereum community cares about is that these validators don't have like intense hardware requirements. So you can imagine like, hey, if for example, with a chain like Solana, they have very few nodes. They have very high hardware requirements for the chain, and that's how they increase the TPS. But in the Ethereum setting, we're really bottlenecked by like the minimum hardware requirements of the validators that are performing the chain. Now, simultaneously, the Ethereum community kind of recognizes that, at least in the L1 market, it's really important for Ethereum to scale to much higher TPS, like 10,000 millions of TPS. So there are these pretty influential Ethereum researchers like Dankrad who are proposing these EIPs where they want to increase the gas limit by 100x. But then again, there's this open question of how do we increase the gas limit by 100x while maintaining these values of decentralization? So this is where real-time proving comes in. So the EF and the Ethereum community in general is really excited about real-time proving right now because it's able to solve this exact problem. Instead of increasing the hardware requirements of the validators, you can instead generate a zero-knowledge proof of the transactions that are being executed. And then you could imagine even the weakest validator in the network, maybe even a Raspberry Pi that's like only $35, could be verifying 10,000 transactions per block. So we've kind of broken this trade-off of like the hardware requirements and the number of transactions that are possible to prove with zero-knowledge proofs. And there's actually a lot of excitement about this idea, even outside of like more of the nerdy types in the Ethereum community. So for example, like Kathy Wood and one of her analysts suggested that this was a really promising direction for Ethereum and that it was a great way to become competitive in the L1 landscape. So to be pretty concrete, what does real-time proving actually look like in the block building pipeline? Well, we keep most of the things the same, but the main thing that changes is that now, when the block builders send the block to a proposer, instead of just sending the block, you could imagine they bundle it with a zero-knowledge proof. And then downstream of that, all the validators, instead of re-executing the block, they just verify the proof. So just with this one change alone, we now have a situation where verification of the transactions just takes milliseconds. It's going to enable us to scale the gas limit by 100x. And you can imagine that if this technology exists, we could even be more ambitious with the L1 scaling roadmap, achieving even more ambitious targets. Now, personally, I think real-time proving is one of the most key technologies that we need to develop over the next year for Ethereum to be on path to becoming the world computer. When we increase the TPS, we're going to be able to host more ambitious DeFi applications like CLOBs. We're going to be able to settle more rollups that are operating at a higher TPS to the L1, which will be really great. But simultaneously, I do want to emphasize that there are other things that we need to improve on as well. For example, we need to reduce the block times. We need to increase the DA capacity of the L1, and also solve L2 interoperability and finality. Nonetheless, at Succinct, as a company really focusing on zero-knowledge proofs, I think this really strong motivation, I think not just with our company, but in the ZK space generally, this real-time proving problem kind of became like the space race of the ZK space. So this is like something that many, many teams are focusing on solving. I think at Succinct in particular, we felt very naturally suited to work on this problem. One of the key open source projects we maintain at Succinct is this SDK called SP1. It's something known as a RISC-V ZK VM. The high-level explanation of what it does is it's able to take any existing Rust or C code and run it inside of a proof system to generate a proof. And SP1, because it's able to do that, has become really popular with developers who just really want to go 0 to 1 with ZK as fast as possible. Because when you use something like SP1, you don't need to know anything about cryptography. It's super easy to set up. And you can also reuse libraries like Alloy or Foundry and the existing Rust Ethereum ecosystem. We actually have a lot of adoption. We're used by 35+ protocols. We have thousands of GitHub stars. So overall, we were like, hey, SP1 was really great because it made using ZK easy. It made it very performant. But what if we could also bundle in this product the ability to prove Ethereum in real time? And in general, the improvements we would make for proving Ethereum in real time would also generalize to other computations, which is what made it a really interesting research problem for our team. So one thing that we benefited from, we kind of had a jump start, which is that we were already using SP1 to prove a lot of Ethereum blocks for L2s. And this was actually really easy for us to do. And I have to do my shameless Reth plug. But you basically just compile Reth to a binary, to this standard called RISC-V. It's an open source ISA supported by most compilers like LLVM. And you literally just take this binary and you run it in SP1. So we kind of already had this end-to-end pipeline for proving Ethereum, and it was really easy. Now, one difference that's worth noting about this pipeline compared to like the past is that a lot of the teams that you might be familiar in ZK, like Starkware or ZK Sync or Scroll, what they did is they actually like kind of embedded the binary into the proof system itself. Right? So they actually like kind of designed a circuit in a ZK proof system that was specifically designed for proving Ethereum. But one thing that's really worth emphasizing here is that we're able to take existing code, like the Reth execution client, and just run it in SP1 and get a ZK EVM out of the box. Anyways, so for the past 6 months, we developed a new version of SP1. It's actually called SP1 Hypercube. And we kind of, in the early days of SP1's development, we were really focused on usability and cost. But when we realized that real-time proving was a really big thing that we need to optimize for, we realized that a lot of the design decisions and the engineering decisions we made with architecture could be adjusted to be much more performant with real-time proving. So I don't want to get too deep into the technical details, but we had to do like a lot of moon math engineering to make this happen. So for example, on the proof system side, there are really popular existing proof systems, such as Starks, that are used in a lot of the most popular ZK projects. we kind of had to replace that with some new math that our research team developed. We really had to push our data center operations. Right now, we run like thousands of GPUs on AWS to coordinate really large proving jobs, but realized that the GPUs on these clouds are too slow. So we actually had to scale up like these third-party data centers. We had to use like consumer graphics cards, figure out how to optimize the GPU performance on them, and really like pick out all the low-hanging fruit of performance. And then on top of that, there's a bunch of stuff like pipelining, scheduling, all the classic performance acceleration stuff that you have to do. So this is a visual that we made visualizing our release in May 2025, where we released an early preview version of SP1 Hypercube. And what this animation is showing is it's actually showing us proving Ethereum blocks in real time on a cluster of 200 GPUs in Nebraska. And what each of these bars are showing, it's showing one task running on one GPU that's like processing a section of the proving workload. And oh, sorry, I guess I can only play it once. But so each of those lines was showing a proving task that was running once. And you can see that we're running many of these tasks in parallel. The tasks are constantly streaming in. And to even get it to that latency took a lot of engineering on our end. And you could see that for some blocks, we were able to prove them under like 6 seconds. Now, these are some concrete benchmarks we ran across 3 months of blocks on Ethereum from April to May. We like uniformly sampled, I think, around 10,000 or 100,000 blocks. And we ran this benchmark where we basically ran SP1 Hypercube on these 200 GPUs to see like how close we were to this objective. So as you can see, we were actually able to prove 93% of the blocks under 12 seconds. Now, you might be asking, like, what is going on with the remaining 7%? Well, what we found is that actually for the remaining 7%, the main problem wasn't that SP1 Hypercube was too slow, but it was rather that the Ethereum gas pricing schedule was in some ways divergent from the costs our prover was paying. So for example, there's certain precompiles on the EVM which are really expensive to prove, but they're not properly priced in the gas schedule. So just by adjusting this gas schedule, we think we could get this very easily to 99%. And it's also worth noting that these are benchmarks from a few months ago. We've improved the performance a lot by then, so that should help as well. So I think I really want to emphasize that this real-time proving objective was kind of like a moon landing moment for ZK. And I think if you asked many people working in this industry a few years ago if this was possible, they would tell you it probably wasn't. For some context, in 2023, when a lot of the first ZK L2s came out, the amount of time it took to prove an Ethereum block was on the order of tens of minutes. But with each generation of new ZK technology, we were able to get an order of magnitude improvement on latency. So you can see with SP1, which was released around February of 2024, we got the proving down to a few minutes. With SP1 Turbo, which came out around December 2024, we got it down to tens of seconds. And with SP1 Hypercube, which came out early 2025, we finally got it under 12 seconds. And I think in general, there's kind of this Moore's Law type of behavior going on in ZK right now, where with every generation of technology, we are not seeing the gain stop. There's a lot of low-hanging fruit. And I think it would be potentially not surprising if we got real-time proving down to even a few seconds or less than a second within 12 months. Now, in terms of the economics, I think this is something worth discussing because if the amount of money it took to generate these real-time proofs was unreasonable, perhaps we could not use them for Ethereum L1. But even today, the actual economics of real-time proving are really good. The amount of money you need to set up one of these clusters is only around 300K today. And we think that with more performance optimizations, we could get it to around 100K. Now, there's also some variable electricity costs that need to be paid for. We haven't benchmarked them, but we don't think that they're going to be a huge bottleneck. But in general, I think the economics of real-time proving are very approachable and will only continue to become more and more accessible. Now, in practice, while this technology is being developed by many ZK teams, there is an open question of how we actually integrate this technology into the protocol. I think earlier in my talk, I described a bit about how we might insert it into the block builder pipeline, but I did not answer many questions. For example, who is going to provide this proof? Where are they going to get it? Will we enshrine one ZK VM, or will we have many ZK VMs? And are there any weird game theory or mechanism design problems with introducing this into Ethereum? So there's a lot of people looking into this right now, especially since the EF is so interested in it. And one interesting problem that I think people immediately realized is, how do we solve the problem of block builders adversarially choosing blocks that are really hard to prove to halt the chain? So this is like an example of like a technical problem that we need to solve. Now, one proposal that I've already seen is this idea of forcing the block builder themselves to actually introduce the proof into the pipeline. And this would be kind of a good thing to do, because it would align the incentives of the block builders with the chain itself, which is to not halt. So that's one interesting idea. Now, in terms of how to get the proof, one potential option is that these builders actually set up these clusters themselves. I said that it was around 300K. Maybe it's not crazy for these people to be operating these data centers. Now, another option is we could create an external protocol, kind of similar to MEV Boost, where we externalize the proving work itself to a marketplace. So one emerging concept in blockchains right now is this concept of prover networks, which are these permissionless two-sided marketplaces for proof generation. And you could imagine that these Ethereum builders plug into such protocols. Maybe they have assets or predefined off-chain agreements to outsource these proofs to these data centers. So in terms of the flow, you could imagine it something like this. So these builders are already running a code to build these blocks. They could run a sidecar similar to MEV Boost, like maybe let's call this ZK Boost. This external protocol could actually conduct an auction where many provers around the world are bidding on these proofs and generating them. If you have an auction, one thing that's great is it's a naturally competitive market. So these people are going to, over time, drive the costs down, drive the latency down, and make this much more affordable for users on the L1. Then you can imagine the prover network enforces that these provers have to generate the proofs within some deadline, maybe a few seconds. And you can imagine then that proof gets sent back to the builder, which gets bundled before they send the result to the proposer. So that's one potential way this could be all integrated in Ethereum. But again, I think these are really open questions, and they need to be discussed by the community. So that's about the end of my talk. I think I covered everything I wanted. But in general, the key things I wanted to focus on is first, that real-time proving is this really incredible technology that's being built by the ZK teams right now. And I think it's going to really solve a lot of the scaling problems that we're having with the L1 right now. The technology is in some ways already here. SB1 Hypercube, the latest release of our ZK VM from Sysynced, is already able to achieve 93% of Ethereum blocks. And then finally, I think there's a lot of open design decisions and research questions that we need to solve related to the mechanism design and game theory of how to integrate this into L1 and make sure it's as robust and reliable as possible. Cool. That's about everything. If you have any questions, now would be a great time to ask. Thank you so much.
Yeah, great presentation. So, you're talking about all these real-time proving, right? We can see that right now, probably we can already achieve super fast proof generation. Then, regarding the cost, can you share some data points, for example, for the past few months and probably for the next few years, how cheap we can achieve when we do the real-time proving for all the L1 transactions?
Yeah, that's a great question. So the EF actually has this website called ethproofs.org, if I remember correctly, where there's actually public continuous benchmarking of how expensive it is to generate these ZK proofs for Ethereum transactions. I think right now, the average proving cost ranges between 1/100th to 1/10th of a cent per transaction. And depending on the gas limit of the blocks, depending on what chain you're on, these things change, and also the transactions that are being proven. But I'm very optimistic that for the average L1 user, this is already a technology that is going to be very affordable, and it's almost going to be unnoticeable compared to other costs like DA. Yeah.
Hey, thanks for the call. I was wondering, the 300K, is it per year, per month?
It would be like a one-time cost. So you can imagine, let's say you need 30 GPUs or 50 GPUs to prove Ethereum, it's just like that times the number of GPUs you need, the number of motherboards, the number of RAM sticks you need. That's kind of how we're getting the 300K number.
So it's on premise. It's not rented from the cloud.
Yeah, in the cloud, actually, we found that the markup is like insane, largely because NVIDIA actually like nerfs the cards on the cloud intentionally to get more margin. So we found that if you use these consumer graphics cards like the 3090s or 4090s that are quite available, you can get great cost efficiency, and it's just much more affordable. It's kind of brain dead not to do it. Yeah.
I think it's only been since this week, since you guys launched it, but has there been anything interesting that's taken place from the launch of the Prover network?
Yeah, there has been some interesting market behavior. I think at first the provers were competing, but now that the provers are getting a little bit more sophisticated, I think some of them are like colluding to like make the price a bit higher, which is something we observed. So we're trying to onboard more provers, encourage more perfect competition. I think it's always really interesting to deploy these things in the wild with real money because you start to observe these behaviors. I think it'll take some time for us to nail it, but the prices on the network are actually already very competitive with our like Web 2 equivalent APIs. Yeah.
I have a question about this 7% of blogs that you cannot prove in real time. What exactly is the precompiles, or what exactly the opcodes exist in these blocks that you cannot do?
Yeah, so in ZK VMs in general, even if you just think of it in terms of computation, there's different costs compared to like just real hardware costs. So for example, on a real chip, when you move data around, you actually have to like think about how far is the data. Like, am I going to the registers? Am I going to L1, L2, or like just RAM? In ZK, like all of that is not true. There's no concept of caches really. It's just like the amount of time it takes to store value and retrieve value. So that's already very divergent, where like storage in general is like already mispriced. In particular, with like hash precompiles like Blake, 2, SHA, and Ketchak, you have to be really careful. Because right now in SP1, we have accelerators for SHA and Ketchak, but I think we're just in progress of implementing one for Blake 2. So when users on the L1 spam the Blake 2 precompile, it's really easy for the proving costs to explode and the latency. So these are the type of like, you kind of have to like whack-a-mole all the problematic opcodes and stuff and solve them in the ZK system and also in the pricing layer. So that's what we found.
Hey, really great talk. I'm back here, by the way.
Oh, okay, what's up?
You've thoroughly convinced me that we're making great progress towards real-time proving. The one thing that still concerns me a lot about the ZK work is the potential for soundness errors. This stuff is so incredibly complicated, and like I'm personally unable to like vet the circuits myself, right? What are you doing there to like convince me that I'm not able to generate a fake proof, for example, very efficiently that shows that all your money was transferred to me?
Yeah, I think this is a really great question. Yeah, I think in practice, many ZK systems that have been deployed, there have been bugs found in production, and there's no reason not to believe that this wouldn't be true in the future. I think one thing that is changing right now that is really promising is the development of formal verification tools and automatic bug finding tools. The EF is very serious about this, actually, and they're funding a lot of really great work and really great formal verification researchers to discover these bugs. I think even in the past 6 months, these tools have gotten a lot better. And I think in particular with Picus, which is a determinism checking tool from Verdice, they found a bunch of bugs using that tool. I think there's another team from Europe, I'm forgetting their name, who also built a fuzzing tool that found some bugs. But in general, if you want to get the perfect soundness, I think formal verification is the ultimate answer. It's actually not that much money to generate lean proofs of these circuits and verifying that they're correct. It's actually not that out of scope as well to formally verify the proof systems themselves and the fact that like the Rust code is secure in terms of soundness. So I think that is the #1 way we can get to 100% confidence that these systems are secure. Cool. Thank you. Do you want me to bring this?
Awesome. Thanks so much. John will be here in the hall. If you guys have any other questions, you should definitely find him and ask. Next up, we have Michael Chen with Category Labs. He'll be talking about Monad, BFT, and then doing a live demo. So welcome him up.
Thank you. All right. Hello, everyone. My name is Michael. I'm from the consensus team at Category Labs. Really excited to be here today to present to you Monad BFT. Just as a little background, Monad BFT is a variant of the pipeline hot-stuff protocol. To those that are familiar, DMBFT, fast hot-stuff, and Jotion are all variants of the pipeline hot-stuff family. We chose to further optimize and advance pipeline hot-stuff because they first offer high throughput, they have low finality latencies, and they're very simple. Their high throughput comes from the fact that you're pipelining your consensus rounds and having the next leader collecting the votes for you. The finality is achieved as soon as you get QC over QCs, so in 2 rounds from your original proposals. And it's very simple. You have a fan out, fan in, and every round of consensus will proceed like that. So that's the first version of BFT that we implemented, which is a variant of fast hot-stuff. And here's what we have observed on testnet. So Monad testnet is a validator network with 99 globally distributed validators. But as you can see on the proposal history diagram, every skip blocks sort of appear in back-to-back pairs, right? There's only one offline leader at that time. It's not actually 2 leaders timing out back-to-back. But you do see 2 skip blocks whenever there's only 1 leader offline. So that got us thinking, why, right? And I want to show you and help you to build intuition on understanding why that's happening and how Monad BFT solves that. So just to provide some background on pipeline hot-stuff. Pipeline hot-stuff occurs in this one-to-all, all-to-one, fan-out, fan-in fashion. So every round of consensus, there's 1 leader globally elected. In this specific example, that's Alice for round R. It will construct a block, Raptor cast it to the entire network, and the network will cast its vote to the next leader. Just for some more backgrounds on RaptorCast is also a consensus/network advancement by Category Labs. It features a 2-hop network message for block propagation. On the first hop, the proposer will Raptor encode its own block and assign the chunks to all the validators for a second layer rebroadcast. It is efficient and also equitable because everyone is contributing upload bandwidth according to their stake in the validator set. OK, so back to pipeline hot-stuff. After Alice sends its proposal to all the network casts their votes to Bob, which is the leader for the next round. Bob will create what we call a quorum certificate, or QC. That's essentially an aggregation of all the votes that has been casted on Alice's block. It is a self-contained proof that enough people have seen and agreed to vote yes on that block. After collecting that QC, Bob knows it's its turn to make its own proposal, so it will repeat the same pattern of broadcasting it to the network. Everyone will see Bob's block. If they agree to vote yes on it, they'll cast the vote and send their votes to Charlie, which is the R+2 leader. So this really simple fan-out, fan-in fashion is what powers pipeline hot-stuff. The message complexity of pipeline hot-stuff is obviously linear. You are only sending and processing linear messages per round of consensus, and that's really crucial to reaching a higher validator count and reaching globally distributed consensus. Just to give you more intuition, I'm going to show you a quick animation of how pipeline hot stuff works. So this is a network configuration of 4 nodes, and the leader schedule goes counterclockwise. So right now, everyone casting their vote to node 4. Node 4 is sending out its proposal, and it will follow this pattern for eternity, hopefully. But that's not always the case. There are situations that can cause a leader to go offline. A leader might choose to delay its proposal to capture more MEV to pack more transactions into its own block. So let's look at what happens when there's a timeout. Back to the first example, Alice is making its own proposal to the network, and the network is casting their votes to Bob, the next leader. But here, Bob is offline. What will happen is the network will have their local timer that's timing every consensus round that they locally see. Once they hit the timer, they'll send a timeout message to every other node in the network. So this timeout process is actually quadratic. What the actual round they'll time out first is actually Alice's round, because every leader has 2 responsibilities in every consensus round. It's responsible, 1, for collecting votes for its previous round, and 2, making its own proposal. So in this case, Bob is offline, but we're timing out Alice's first because Bob has failed to collect the votes for Alice. After everyone has timed out Alice's round, they will proceed to time out Bob's round. So that's why you get the back-to-back pairs of timeout round or skip blocks in the first animation that you see for testnet. After it's all collected and we finally reached an online leader, Charlie here, Charlie will build his own block. What's interesting to note here is that the block Charlie will build will not be on top of Alice's block. And that's because there's no quorum certificate formed for Alice's block. That's sort of the artifact of the fact that we are sending all votes to Bob. So what Charlie will do is build off its block off of the highest QC it has observed, which is over block R minus 1. So essentially what we've seen is a tail fork, a forking around the tail of the blockchain. Even though Alice is an honest leader, its proposal got enough support in the entire network, the block got abandoned only because Bob is offline. Just to click into more why tail forking is bad. First, it's terrible because it opens an MEV exploit. In a previous example, we were looking at how Bob, as a benign offline leader, can abandon Alice's block. It's also possible, as a sophisticated attacker, to intentionally wait for the previous round to time out and intentionally not to collect votes for your previous round so that you can unbundle their block and capture the MVE opportunities in your own block. That is awful for pipeline hot-stop protocols. Second, obviously, there's lots of rewards for Alice. Alice has done all of its validator duty, but it's unable to capture the rewards. It's bad for network throughput, and it's also bad for UX because now, because of tail forking, we need 2 rounds of consensus to gain confidence on the block's finality, whereas without tail forking, we only need 1 round. So Monad BFT aims at solving all of these. Most notably, we're providing tail forking resistance. It's a very strong guarantee that the honest proposal with enough support never gets abandoned. On top of that, since we're only modifying the unhappy path of pipeline hot stuff, we inherit all the good performance guarantees on the happy path. Namely, those are optimistic responsiveness, where the protocol progresses at network speed, and linear message complexity on the happy path. So just to give a little more intuition on how Monad BFT achieves tail fork resistance, we are including 2 more fields in the timeout process, namely tip and tip vote. Tip is the latest consensus block that you have seen and agreed to vote yes on it. and tip vote is a vote signatures that you will cast on that block. So if Alice's block or any validator's blocks has gained enough support in the network, enough support meaning there's enough validators agree to vote on that, the next leader is forced to either form a quorum certificate directly from a supermajority of tip votes, or it's forced to repropose the original highest tip, which in this case, Alice's block. Only in the case where Alice's proposal doesn't reach enough support will the next leader be able to move on and make its own fresh proposal. So that's how we are providing tail fork resistance, is by forcing the next leader to either form QC or repropose or otherwise prove that the previous leader's block didn't gain enough support. Now, Monad BFT is live on testnet 2. It's a larger, even larger validator network running Monad with over 180 validators globally. As you can see already, on the proposal history, we've eliminated the back-to-back timing out of skip blocks, and we are always salvaging the previous rounds. Now let's shift gears a little bit and talk about on engineering how we are implementing Monad BFT. We really took the idea of functional core and imperative shell in our design, where the core of our consensus client is Monad state that captures all of the core consensus protocol. It's purely functional. If you give it the same pre-state, the same inputs, it'll always emit the same post-state and same output. And it has completely no side effects. It's not sending any network messages directly from Monad state. It's not arming a timer from within Monad state. All of the side effects are handled by this imperative shell, which what we call the executor. So the run loop of Monad node or the validator client is really simple. There's really three things that we need to do over and over again. The first one being fetching an event from the executor. Second, passing that event to Monad state for execution and to update Monad state. And third, if there are any emitted commands that are side effects Monad state want to apply to the environment, we'll pass it back to executors for execution. So as a concrete example, you will receive, let's say you receive a proposal from the network that will be emitted from the executor in the form of an event. You pass that to Monad state through this update function, and Monad state, if it agrees to cast a vote on it, it will emit a router command, which is an instruction to the executor to send a vote to the next leader. There's several benefits with this design. First, it makes our code very comprehensible, the core consensus code. The inputs and outputs are very explicit in our code in the form of events and commands. It's perfectly deterministic, given the same input and pre-state. We will always get to the same post-state and outputs, and there's completely no side effects in Monad state. And we took this one step further and think about how we can increase debuggability and testability through this design. And that's why we create Mock Swarm. Mock Swarm is a simulation environment where we are only thinking about virtualized time. There's no wall clock timer involved. There's no network communication involved. That allows us to simulate many rounds of consensus very quickly and trigger different code paths in the core consensus protocol. So concretely speaking, we have a globally serialized order of events that's in the form of this event priority queue, and it's ordered by timestamps. Every time we'll pop the first event off of the queue, pass it to corresponding mock node for execution, and the result will get appended back to the queue. So the mock node, the difference between a mock node and the real Monad node, the validator client, is that the executors are slightly different. Instead of sending packets over the real network, it's emitting an event to to other mock nodes and for them to process it. The next thing we want to solve is how to build intuitions on consensus protocols, because they can be quite difficult to understand concretely. And that's why we built Monad Viz. So now I'm going to show you a quick demo of what Monad Viz is, and hopefully that can help you build more intuition around consensus too. So if you still remember, at the very beginning of the talk when I was showing the happy path, we saw the same diagram. It's not just an animation of the consensus protocol. It's actually Monad state, the core consensus code, compiled into WASM, and is running live in your browser. So here we can just see the nodes exchanging messages with each other. There are a lot of things that you can configure in this network. You can configure the number of nodes. You can change how the network latency profiles have dropping messages to different states, making state go completely offline, and there are just various things like network disturbance you can introduce to this simulation environment. It is also completely generic that nothing in mock swarm or Monad Viz is specific to Monad type events. If you have a consensus protocol, you are able to wire it up and visualize what's going on in the network. So what just happened now is node 4 just went offline, and people start timing out and send timeout messages to each other. Now, even though it's node 4's round to propose, it's unable to do so because it's offline, they'll time out again. But even though there's 2 rounds of timeouts, rest assured that node 3's proposal got salvaged because everyone has seen node 3's proposal, and they'll form a QC locally. So when it's finally node 1, that would be Charlie in the first example. When it's their turn to propose, they'll extend the honest leaders block. Just one more thing I want to show you with mock swarm is that, or with Monad Viz, is that you can actually go backwards in time. So if I were to go forward, it would look like proposal going out. I can actually go backwards in time, like so. And that's not a feature of mock swarm. Mock swarm, we never take snapshots of any state, so things will only go forward. This is actually enabled by so every time you drag the slider from the future to the back, it's actually running a resimulation from t equals to 0 to t equals to your new tick. And that's only possible because Monad state is perfectly deterministic. Then you are able to see this backwards animation. So that's the end of the demo. If you don't mind switching back to the slides. So Monad BFT paper is available on archive. Feel free to check it out. We also feature a few blog posts on Monad BFT, more technical details, and on Monad Viz, specifically the visualization framework. There are also RaptorCast blog posts to check out if you're interested. Monad BFT just went open source this week, so feel free to check it out. Monad debugger/Monad Viz is what I just showed. You're free to make any changes to the network. OK, that concludes my presentation on Monad BFT. Thank you. I'm happy to take any questions.
Hey, Michael, thanks for the wonderful presentation. How do you prove that? How does a round leader prove that they have, like the previous round does not have a quorum certificate? If you do this optimistically, then how are you doing this with low latency?
So I'm not sure. OK, I'll try to do an explanation. Just let me know if that makes sense to you. During the timeout process, every node will share the highest quorum certificate they have observed, and the lack thereof is the proof that there's no quorum certificate formed, if that makes sense. Thank you.
Yeah, so my question is that, right now it's a pure theoretical analysis, right? I believe the Monad testnet already running for some time. So based on the sort of the real data points for the testnet, what kind of like the maximum number of nodes we can expect for Monad Midnight in the near future? And also in theory, so what kind of the best latency we can expect like once the Monad Midnight is live?
So for testnets, for the two testnets that we have, as I mentioned, one have 99 validators, and the other one have 186, I believe. That is the network size we're currently comfortable with shipping. And in terms of latencies profiles, that really is dependent on the geographic distribution of the nodes. If the nodes are closer together, you obviously get better latency profile, but that's not what we want. What we want is a globally distributed network. So right now, our network is producing blocks at 400 milliseconds, and that's the configurable block time that we want, so that nodes from different areas of the world can get participation.
Okay, I have a question related to your example when you show that A have the quorum certificate in this case, and but how we can trust the nodes that they show like the same? I mean, the honest nodes can be separated to the few groups or as many groups as it can, because like the A can be malicious in this case. So I mean, like how the security property works in the case that A produce few blocks or all of the things around it. What's the math related to the safety? Did it steal 1/3 of malicious assumption? 1/3, I mean, like 2/3 plus 1 honest assumption, or it's changed?
Yeah. So the security guarantee of like Byzantine fault tolerant isn't changed with Monad BFT. You asked a very good question. You're asking about what if Alice is malicious and it's trying to equivocate, and by sending a different proposal to different parts of the network. First of all, it's a slashable offense, and we're able to collect evidence for any equivocation. And second, during reproposal, the honest leader will only repropose one of the original equivocation. And if that's on the assumption that if that equivocation has reached enough support. If it hasn't, it will proceed with collecting a no endorsement certificate, which if you're interested, I'm happy to delve into later. It will move forward with a no endorsement.
Great. Thank you very much for the great talk. I have a question regarding the leader election. What is the current logic that will determine who is the next leader or proposing the next block?
Right now, we are using a deterministic, like pseudo-random weighted round robin. So that's the current leader election protocol that's live. In this visualization, we just use round robin and to just visualize it better, since everything can go counterclockwise.
Thank you.
Thank you.
Nice, perfect. Good, great job, Michael. All right, next we have Brendan Chow with Commonware. He's going to speak to us about Minimmit.
Okay, great, thanks. Hey everyone, I'm Brendan from Commonware, and I'm here to talk to you about our new consensus algorithm that we came up with called Minimmit. And the alternative name for the talk is Consensus for Everyone, because that's me over there on the right. I'm just an engineer. I'm not a researcher. So as we were looking for a really fast consensus algorithm to power blockchains of the future, I was reading all these papers, and I was thinking, oh my God, I'm going to have to code this. I'm going to have to write tests for all these different code paths. Is there something simpler that we could do? It seems like there's a lot of unnecessary messages that are being sent around and so forth. So we set out to write something that was as simple as possible, and I hope I'll go into a little background on consensus in general, and that should basically make the talk more accessible to people who aren't consensus people. Some of the explanations are going to kind of be vibe codey or like vibe explainy. So some of the explanations might not be literally correct, but they should at least be good signposts to help you understand. So we'll go over a quick definition of consensus really quickly. Consensus, I wrote, is every correct replica eventually decides on the same blocks. So replicas you can think of as validators, nodes, that kind of thing. And it's basically saying if you're running the software as intended, you're going to agree on the same blocks as everybody else. There's two other terms you need to know because they'll come back. That's safety, which is the same blocks part, so everybody agrees on the same blocks, and liveness, which is that everybody eventually decides. Talking a little bit about fault tolerance, just again going over some quick definitions. There's correct replicas, which follow the protocol running the software as intended. There's faulty replicas, which try and follow the protocol, but maybe their network connection isn't so great, or they're accidentally crashing for some reason due to misconfiguration or an out of memory or something like this. And then there's Byzantine nodes, which basically have modified the code to run in an arbitrarily evil way. And a lot of consensus algorithms for a long time basically followed the assumption that there's less than 33% of faulty nodes in some way. And so the main trade-off that we made is that we're actually assuming less than 20% of faulty nodes in some way. So this is the main trade-off that we're making for our algorithm, is to basically assume a lower threshold of Byzantine nodes. And I hope you'll see why that trade-off becomes worth it. One more time, just going into some assumptions about the replicas themselves. We basically, in these types of algorithms, we assume that they're all connected to each other and that they can all communicate to each other within delta time. So delta is basically just the time it takes light to go around half the world generally. And you basically bound that. It's basically a bound on the protocol so that OK, well, if it's been long enough, then I time out. Another thing is all the replicas have public-private key pairs, so they can all be identified by their identities and cryptographically signed messages so that everybody knows, OK, it's coming from them. And then, as we said before, we're assuming less than 20% of all nodes are either Byzantine or faulty. OK, so there's a couple things, a couple more concepts to teach you guys before we get into the algorithm itself. The first is the pigeonhole principle. And there's many different ways to use pigeonhole principle, but basically the one I wanted to point out here is if you must vote for A or B and you collect 80% of votes for one of those two things, then you will be guaranteed to see at least 40% of votes for one of the two things. For either A or B, we'll have at least 40% of votes. If you have three different options, then you can kind of extend it a little bit and say you will have at least 40% of votes for A or for not A. So something that is A or something that is not A. Equivocation is just a fancy word for basically saying two different things. So this is what Byzantine nodes can do. They can vote for A and they can vote for B. Now, it's a little bit obvious when they vote for A and vote for B and then tell everybody about that. Generally, what they'll do is they'll tell one person A and tell a different person I'm voting for B. So just keep that in mind. That's what equivocation means. And then a really important property you'll see is the quorum intersection property in a lot of these consensus papers. So it helps us form a proof by contradiction. So let's say, again, we are voting for either A or B. Let's say A is the orange thing on the left side, and you have more than 40% of votes for that, and B is the green thing on the right side, and you have more than 80% of votes for that green thing. So that can only happen if you have equivocation from more than 20% of the replicas, as you can see in the middle. That's the only way that you can both have 40% of votes for A and 80% of votes for B is by having more than 20% equivocators. But as we said in the beginning, we're assuming that less than 20% of all nodes are Byzantine. So that would basically break our assumption. And so this basically forms a proof by contradiction. I'll say that one more time. So basically, you can't have 40% of one thing and 80% of a conflicting thing unless you're breaking the assumption about how many Byzantine nodes there are. OK, so getting into the algorithm itself now, just some basics is that it's view-based or round-based. There's many different terms for this. So there's one leader per view and one round of voting. And each view will result in a block and or a skip, where a skip is basically no block. So it can actually result in both. We'll talk a little bit more about that later. I've said it several times now, but we're assuming less than 20% of all replicas are Byzantine, and also that more than 80% are correct. This makes sure that the safety and liveness properties that I discussed in the beginning of the talk are not violated. OK, so getting in the first part of the algorithm, you either propose or you wait. So in each view, there's a leader. And if you're the leader, you propose. So I say broadcast lead. And called lead is basically some message that you're sending out. By broadcast, I mean you send it to every other replica. So if you're the leader, you broadcast the block to every replica with this message called lead. Basically, I'm the leader, and here's the block for view V. So that's the V and the B. And then everybody else just waits. They wait to receive the proposal. It's set to 2 delta for some reasons. Delta, again, is the maximum time it takes to send a message to someone. For technical reasons, it's 2 delta. But the point is mostly that you start a timer, and you wait to get the proposal from the leader. Then, as everybody else, you either vote or time out. You either receive the valid block or you don't. So once you receive the block from the leader, you broadcast. Again, that means just send to everybody else all communication. You vote for the block. You say, yes, this is a legitimate block. I won't go into verifying the block, because that will depend on the blockchain itself. But you run whatever logic you need to as your application-specific blockchain needs. And then if it's a valid block, you'll vote for it. Otherwise, if you don't receive a valid block in time, what you'll do is you'll broadcast a vote for no block. So this upside-down T thing is basically, that's a special symbol for null block. So yeah, you can think of that as no block. The block can also point to its parent and all those other good things that blockchains normally have. OK, so how do you actually, once everybody votes, how do you actually progress and finalize? It's pretty simple. Once you see 40% of votes for something, you can actually move to the next view. So you start the whole thing over. Check if you're the leader. Otherwise, you start your timer. And in addition, when you see 40% of votes for something, you also broadcast this cert message. And a cert message is basically just a collection of votes. In the simplest possible system, it's just an array of those 40% of votes that come into you. Maybe you have some sort of signature aggregation, which can do it in a little bit more compact of a way. But essentially, you can just think of it as you're broadcasting that collection of 40% of votes to everyone. And so once you see 40%, you've moved to the next view, and you can start processing the next block. If you're the leader, you can start proposing the next block. If you see 80% of and then I should explain what the asterisk means. The stars basically just means it can be a block or it can be a null. So in the previous slide, we talked about this special timeout, voting for null. The asterisk just means it's either a block or a null. So for either of those, you can, if you see 40 null or you see 40 block, then you can move to the next view, and you broadcast the certificate to everyone, which is a collection of the votes to make sure that everybody has all the necessary information. If you see 80% of votes, and remember, you've already moved on to the next view at this point, because to see 80% for something, you must have seen 40% for it. If you see 80% for it, so this will be in a previous view now, because you've kind of moved past the current view, but you're still waiting for these votes to come in from that old view. If you see 80% come in, then what you can do is you just finalize the block. You know it can't be usurped by anything else. And because it's finalized, all of its ancestors, so its parent and parent's parents, are all finalized implicitly. And then one more thing is that, as I mentioned, you broadcast the certificate of 40% votes when you get 40% of votes. Maybe it's the case that someone sends you this certificate before you get all the votes, and so that's why I added this. You either get 40% of the votes or a certificate, which contains 40% of the votes. You will also broadcast a certificate to everybody who hasn't sent it to you. And you just have to do that once. You don't have to do that over and over again. OK, and then that's basically the entire algorithm, honestly. There's one more wrinkle here, which I'll explain, and maybe this is the most complicated part. But basically, yeah, I guess in this slide, I implied that either you're going to vote or you'll time out. It's like, OK, if you see the block, you'll vote the block. Otherwise, you'll vote for null. And if you're an honest replica, you should just do that. There's one more case in which it's OK to vote and then also vote for the block and then later vote null. So that's this case I'm about to talk about. And you don't have to, if you already voted no, if you already timed out, you don't have to worry about this at all. It's just if you cast a vote and you're still stuck in that view, then you might have to also consider voting null. So I call this abort. So if you see 40% of votes for something that is not B, so that's the exclamation B is not B, that is either basically a null vote from somebody or a vote for a block that is not the same block that you voted for, then it's actually OK to then also broadcast a null vote to everybody. So this is basically protecting if you imagine that a malicious leader sends a different block to every replica, then you'll basically get a different vote for a different block for each thing. And there's no 40% quorum on anything. But you will see that other people have not voted for the block that you have voted for. So that's where the not B comes in. And then basically this prevents a leader who equivocates a different block to each participant from stalling the network, because everyone will eventually vote null, and then eventually there will be a null certificate that you can move on from. OK, so just an overview, basically, of the whole protocol in one slide. I'll just go back through it again. Basically, there's a proposal. Every time you enter a view, if you're the leader, you propose a block. Then, if you see the block in time, you vote for it. Otherwise, you vote for null. There's this abort thing, which is only if you've voted and not timed out. Then you have to worry about this. But it's basically if you ever see 40% of things that conflict with your original vote, then you can also send a null vote. Then every time you see 40% of something, either a block or a null certificate, or either a block or a null, you form a certificate, which is just a collection of those votes. And then you send it to everybody else, all to all. And then lastly, if you ever see 80% of votes come in, so you're already in a future view, but you might see votes come in as you're working on your next view, then you can finalize that block and all prior blocks. And hopefully that happens every block, but there can also be runs where you haven't finalized things and you must finalize them implicitly. So just looking at a quick example here, if you're a visual person, so views progress from left to right, basically, and you have the genesis block, which implicitly has, everybody agrees on the genesis block. And I guess the solid green blocks are the ones that get finalized directly, and the green blocks that are white in the middle are blocks that are finalized implicitly. And then the other boxes are basically certificates that come, but are never finalized in the chain. And then the black stuff on the right is basically stuff that's in your working view. So it hasn't been finalized yet, but it's sort of like the working group of stuff that you're working on. The yellow stuff you can sort of drop from your memory as a validator. And I guess the important thing here is basically what it looks like is you're going to have one nullification certificate or a block certificate in every view. So you have to have at least one box in every view. And you're basically charting this course from left to right of what one of those things is like the valid thing in that view. So it's either a skip, which is like a nullification certificate, or it's a block. And you can finalize things when you know that everybody else, all other replicas, are going to see that thing in that view. So you can think of it like, for finalized blocks, there's a bottleneck there, where that's the only path you can chart through that thing. That's the only path you can chart through that view. That's the only thing that anyone will ever see a certificate for in that view. And so to finalize things, you don't even have to tell people that you're finalizing. You just know, like, I see this in this view, and no one else will see anything else in the view. So I guess going into proofs, in quotes, or kind of argument. So bringing back the ideas I talked about at the beginning of the talk, by the 80-40 quorum intersection property. Basically, if there's 80% votes for something, there can't be 40% for something else. So if you see 80% of votes for a block, then you know no one else can ever see 40% of votes for a different block or for a nullification. So no certificate for anything else. That's why you can finalize it. And then for liveness, basically, you just have to make sure that you can proceed with, well, if you have a correct leader, or an honest leader, they'll correctly distribute the block, and everybody will vote for that block, and you'll be able to finalize it with at least 80% of the vote. For a faulty leader or a Byzantine leader, basically, I'm just illustrating here why you can expect to move on from that view eventually. And maybe nothing will be finalized in that view, but as long as you can move to the next view and something eventually gets finalized, each finalized block implies entire history of finalized blocks. So just based on time, I won't go over those last 2 points. You can ask me about it later, or left as an exercise to the reader. OK, so just to go over kind of what is good about Minimmit. First, it's simple. So there's only these 3 message types, which is, I think, better than what is considered state-of-the-art, basically. In a lot of constructions, the vote, maybe there's 5 message types, because voting for a block is maybe slightly different than voting null, or a certificate for a block is slightly different than a certificate for null. But even that, there's fewer messages than all other constructions that we know about. It's fast, so it can finalize blocks in just a single round of voting, which is the leader dispersing it and everybody voting. So in one round trip, you can finalize blocks. Decide an 80% of the weight. So that is basically tied with state-of-the-art, as far as I know. And then what's, I guess, faster than state-of-the-art is that you can go to the next view after only 40% of all nodes respond to you, which is faster than state-of-the-art. Typically, you'll need like 60% or something like that. So the finalization time is basically state-of-the-art, but the block time is faster. And then lastly, it's really flexible due to its simplicity and its similarity to a lot of other algorithms that already exist. So something like simplex, which has a bunch of different extensions built on top of it, like, oh, you can do simplex with erasure coding. Here's how. Like, all those different extensions basically also apply to Minimmit because it's in the same family of algorithms. So you can do all these cool things like signature aggregation, erasure coding, and stuff like that. And so, yeah, that's my talk. I'm from Commonware. I said we're the center for kids who can't consensus good but want to learn to do other stuff good, too. And thanks to everybody that's listed here, Paradigm. And we're coming out with a white paper written by Andrew Lewis Pye soon to basically formalize all the ideas here. And then there's also a Quint spec, thanks to Informal Systems for Quint, and Denise Kolegov for writing that Quint spec. Good on questions?
I actually work with Brendan, so but I'm not working on this consensus stuff. So I'm kind of curious. The previous talk, what are the assumptions and I guess properties of Minimmit that are a little different than the Monad BFT that we just saw presented?
That's a good question, and I'm not super well versed in the in the hot stuff line of consensus algorithms. And unfortunately, I had to miss a lot of the talk because I was backstage. But my understanding is basically that it has that fan-out, fan-in property. And while this has the fan-out, it does like a fan-out for the proposal from the leader, and then an all-to-all stage where everybody's doing all-to-all voting. Hot stuff, as I understand, yeah, has that fan-in stage. And there, obviously, Michael talked about there's different ways to kind of get around problems with the centralization, then that can occur when everybody has to push through the same thing.
Just to confirm, as I understand, the message is quadratic, and there is a strong assumption related to the synchronous clock. Am I right? To synchronize the rounds, so it's synchronous consensus algorithm. Am I right?
Yeah, so I guess the first question...
quadratic, it's...
Sorry, yeah. So it has, I guess, within the whole network, since you're doing all-to-all communication, then there's quadratic complexity in terms of the entire network. From the perspective of one validator, you're sending messages to every other validator, so it's linear from the perspective of one person. And then kind of what I said about... hard to go back in the slides, but... oh, nice. What did I say? Basically, you can do stuff like erasure coding that can do this fan-out kind of thing. So there's a lot of problems with a lot of consensus mechanisms where you push everything through a leader, where they have to tell everybody, OK, here's the block. But what you can do is like an erasure coding kind of thing where you basically tell everybody just a little chunk of the block, and they tell everybody else. And so then the leader never, the amount of bandwidth that the leader has to do or that any of the peers has to do is actually constant with respect to the size of the block rather than to the size of the validator set. So you can do those kinds of things that's not built into the original protocol, but it's nice that it's easily extensible in that way that's already been applied to other similar consensus functions. And then you had another question, sorry, that I forgot. Synchronous timeout, yeah. So you do basically, as I was saying, you have to make this assumption about the delta timeout thing. What's nice is that you don't have to sync your clocks, really, because you can't progress to the next view until you've seen a sufficient number of messages. So you don't just say, OK, timeout, I'm moving to the next view. Timeout, I'm moving to the next view if you're not synced up. Basically, you time out, and then only once you see everybody else's timeout, then you move to the next view. And so you do have to get that parameter right. That's like that delta. That's the maximum amount of time you're willing to wait. But after that, it's like if somebody's clock happens to be, yeah, you need clocks to run at around the same speed, but if someone's clock is 10 seconds off someone else's clock, that part actually doesn't matter. Great, thanks.
Nice job. All right, thanks, Brendan. OK, and the last and final talk of Frontiers before we get to the hackathon presentation is going to be Adi with Informal Systems talking about Malikite. So welcome him up.
Thanks. Hello, everyone. I really love the event so far. And kudos to the organizers for having a consensus track. I think that should happen in more of these events. Way to go. Yeah, I'm going to speak to you about Malikite, which is a fast and flexible consensus engine that we have built in Informal to power the next generation of, let's say, deeply decentralized systems. So the motivation for building Malikite is that I feel that crypto and more generally decentralized systems community and industry is stuck in a bit of a local minimum. And what I mean by that is if we step outside of our immediate, let's say, technical bubble, the general audience, they see messages that look very much like the one that I have in Exhibit A. And this is cool. It's perfectly fine. I even encourage it. We should have fun and responsibly enjoy the financial freedoms that are unprecedented, very privileged, let's say. But I have the gut instinct that there's a lot more we can do. And I'm going to oversimplify and maybe even be a bit provocative. But if I do an analogy to the fitness industry, it would be as if the whole fitness industry was about just selling ab belts. And these are super convenient, and you're just at home and you're not doing much. It's the most convenient thing in the world, even. But it's not that exciting to work on an industry that solely focuses on that. Fortunately, the fitness industry has so much more to offer, including hard and difficult things. And people like doing hard and difficult things. They don't always just want convenience. Like, I don't know, CrossFit and barbell training and crazy stuff like ultra marathons. You tell me. But yeah, I have the intuition then that we should be able to do more things. So it's not really enough what we've been doing so far. And we're not done, basically. What I mean by that is we were able to literally do something that is very fascinating and amazing, which is we trained or we were able to teach computers to agree with one another in a highly adversarial setup. And we've been doing that for 10 years or so. And it blows my mind every time I think about it. And I refuse to believe that this is it, that we cannot do more with this kind of primitives and building blocks. So this is my basic message. I believe we're not done with iterating on the deeper level of the applications that we're building, that we can build more highly differentiated applications. What we have today is amazing, but I think we can go even further. And that's why we built Malikite. To be able to build such highly distinctive applications, it takes very, very lean and flexible building blocks to be able to iterate rapidly and learn and so on. Yeah, and that's the motivation for Malikite. The rest of the talk is going to have these three parts. I'm going to focus on a bit the past. How did we start it? Why? Current users or the present. And the third part of the presentation is going to focus on the future. Where are we aiming towards? The origins of Malikite, they lie actually in the StarkNet ecosystem. The StarkNet team is a very talented team. They've been building this very cool L2, and then they realized a couple of years ago that, hey, let's decentralize our sequencer, because that's the next logical thing to do. And while they were doing that, they had a very first principle-based approach. Actually, they did a lot of requirements, research, and they drafted these many forum posts that I encourage everyone to read, the decentralization tag. And they landed on the decision to use the Tendermint consensus algorithm. They basically had two reasons for that, or at least that's my bias about the reason why they chose Tendermint. The bias that I have, and the two reasons are, Tendermint is very well understood in the literature. There's basically one version of it. It's standard. Everyone, or not everyone, but it's very well understood. So theoretically, it's studied. Its operating conditions, performance, limitations are very well understood. In practice, it also has the Comet BFT implementation, which has undergone, let's say, more than 100 years, I'm talking here cumulatively, of practical experience. There's hundreds of chains that use it, ranging from very big ones and very important ones that many of you are familiar with, up to crazy stuff and black swan caliber events like the Luna event. And it put up with those situations. So there's also a practical element besides the theoretical kind of well-understood part of Tendermint. However, their first insight, after the StarkNet team decided to use Tendermint, was, well, we cannot use Comet BFT, even though Comet BFT was the canonical implementation, and it has this advantage that I just described to you, that in practice it's proven in battle. So, and I was actually disagreeing with them in the beginning, telling them, no, maybe you should use Comet BFT because it's quite good. And I still recommend to many teams to do that today. However, they proved me wrong, because actually the thing that they were trying to build could not be built with Comet BFT back then and either today. So to give you a bit of a timeline, how things evolved, these discussions that I told you so far were happening exactly 2 years ago. It was at SBC in 2023, not too far from here. So that was around August. And their first insight, and eventually they convinced me as well, and the rest of our team, that actually they need a fresh implementation from scratch. A few months later, we started in earnest the design and development in Rust of Malikite, what would become basically Malikite BFT. At that point, it was just the Tendermint implementation, so nothing around it. A few months later, in July 2024, we started talking publicly about it, and we realized that this actually this implementation that we're doing, it may scratch an itch that is more general than just what Starknet team is experiencing. And that is the itch of wanting to go beyond what this black box of Comet BFT that is excellent to start with can offer to some teams. Some teams want to build things that are a bit more exotic or different or highly distinctive. So we started to double down on, OK, how expressive and how flexible is this thing that we're building? We don't want to repeat the experience of Comet BFT kind of being stuck with what you have. So we're starting iterating and being more deliberate about API design in Malikite. A few months later, December, we made the code public and open source with Apache license. And a month later, basically, the Farcaster team surprised us that they actually put it in production. And that just blew my mind, because it was a month after the code was open source. It was well tested. It had Quint specs and model-based testing and so on. But it was still really, really surprising. Yeah. The APIs that I mentioned so far, there's actually 3 of them, and this is what gives the flexibility of the consensus engine. There's actually at the bottom one is just Tendermint. It's a state machine of the consensus algorithm, and this is just a library. It doesn't even have state and anything. Then as you go up on the stack of APIs, you have more and more built-in batteries, or off-the-shelf, let's say, included support. And then more and more choices are made for integrators or developers. So at the middle layer, there's an actor API, we call it, because at this level, there's a runtime and different components of the system, such as the block sync, P2P, the write-ahead log, and so on. Each of them is an actor that is communicating with all the others, including the consensus state machine itself is a wrapper. And then at the topmost level, which is the easiest to integrate, but the least flexible, and it's possible to go down on the stack. Once you build an MVP or a prototype at the topmost level, then you can throw it away, and then you build at the lower level of abstraction if you want to differentiate it or you want to build something new or different. The 2 driving principles that have been, let's say, influencing us and inspiring us were kind of a bit more of a philosophical way of looking at what I described so far. Was we want to be able to drive the deep differentiation of applications. So it should be a distinguishing fact if you build with this consensus engine. And if you do not need that, if you're just building something a bit more standard or that looks a bit similar to what we've seen so far, then Comet BFT is still an amazing choice, to be clear. And the second one was to facilitate the growth of applications. Because once you launch, then many teams actually figure out that they're kind of stuck with what they have, and upgradability and so on is pretty tough. So yeah. This was the first part. I'm going to spend a bit of time talking about the users today. It's just 3 use cases, and I'm going to go through them quite fast, actually. It's not the purpose to give you like a technical crash course in the architecture and design of these systems. But they're pretty interesting. So Mother and Pathfinder are two teams from the Starknet ecosystem. They are integrating with Malikite at the lowest level. So they're not using write-ahead log, P2P. They're bringing their own stuff, basically everything, except for the consensus library. This is the first team that started integrating and giving us feedback. The system that they're building, and the reason why they couldn't use Comet BFT, is it's quite complex. So it actually consists of these 3 distributed systems, if you will. One of them is the sequencer, one of them is the L1, and the other one is the execution. And the sequencer itself has to coordinate between these 3. You have to fetch proofs, you have to sequence the proofs into the L1, and you have to enforce updates from the L1 contract into the sequencer. So it's a bit of a recursive dependency, because the validator set in the decentralized sequencer has to be influenced from the L1. Yeah, it's a very interesting use case. The second one I'm going to talk about is Snapchain. This is what the Farcaster team have been building. They went basically from a prototype to production in 6 months. They have a sharded design. And this is also super interesting because there are not many. Even in crash fault torrent models, building a sharded design, it can be very tricky. In BFT, doubly so. So they're basically sharding, they're partitioning user accounts by their lexicographic order, and they associate each user account to one particular shard. And there's many of them. I'm just showing 2 here. These are each a BFT instance or a cluster of nodes, and they also interoperate with the OP mainnet, where they fetch user registrations from and a couple of other critical parts. But their purpose is actually to store user data. It's a backend. And then there's an additional cluster that is called the coordinator. And this guy puts everything together. It linearizes the whole history of all the events across all the shards. This is integrated at the actor level, so at the middle level of abstraction. It's not the top, but it's not the bottom either, because they reuse some things from the engine. The third use case is from the Zcash ecosystem. They're building this since a few months ago, and it's called Crosslink. So the team is Shielded Labs, actually, the core developers in Zcash, and they want to go from the proof-of-work style to a hybrid model. And the problem they're trying to solve is basically to no longer have probabilistic finality, but they want the 10-minute style. They're shooting initially for 10 minutes finalization time, but they're going to go lower and lower as they're gaining more and more confidence. The basic idea here is that validators in the proof-of-stake system, they need to agree on the next safe cut of the proof-of-work history. And the tricky part is that each of them may see different parts of the proof-of-work history, and once they make a decision, they cannot go back on it. That's what finalization means. So once you go on a fork, for instance, height 2 there points to I, you cannot go back to D or E in a subsequent height. You have to stick to that. So it's a delicate decision while they're running the agreement algorithm. The choice that they make as a proposal and the things that they pre-vote and pre-commit on, they have to be safe. Yeah, this is the last. That was the last example that I wanted to share with you. I'm going to spend a bit of time on the roadmap then, on the, let's say, future part and the things that we are preparing. We published this a few months ago, and we're basically now in execution mode. Yeah, the roadmap. It has 3 parts. We have, first, we have improvements in throughput. This is what we call multi-proposer. But actually, the multi-proposer is more of an emulation of a multi-proposer model. And I'm going to get to that in a second. And we hope the code name for this is Muppet, just from multi-proposer. We needed something to be easy to refer to. And we're aiming to have a throughput improvement of 10x. It's more of a vanity metric, to be honest, because no team is actually pushing Malikite to its limit today. So let's see. A second part of the roadmap is the two-phase Tendermint variant. And what this does is actually very, very similar to the Minimmit protocol that Brandon just presented. It's essentially kicking out, for those of you that are familiar with the Tendermint protocol, which has 3 phases. It kicks out the last phase. And it's able to do that safely because the protocol goes from a fault threshold of 3f+1, going back to one of the questions in the public, to a fault threshold of 5f+1. So we're reducing the fault threshold, meaning that we're tolerating less faults. Some teams, interestingly, told us that this is desirable because of restaking and shared security models. And there is increasingly higher confidence that the rarity of slashing events and the rarity of Byzantine faults is quite low. So some teams are willing to experiment with 5f+1 models. The last one is EVM compatibility. We have experimenting with this for quite a while. Actually, the first MVPs we built were in February this year, and we actually built 2 of them. One of them is, how would Reth and Malikite look if it was in the same process? So those familiar with SDK and Comet run in the same process. Ethereum architecture decouples the two, consensus from execution. And that's the Malikite Turbo MVP that we built. This is more for if you want the vanity metric of performance, you're going to be able to push performance better if everything is going to be coupled in the same binary, because you can bypass quite a few, let's say, intermediary abstraction layers. If you prefer a decoupled architecture like Ethereum, then we built a different MVP that we call the layered version. It has the 2 layers, execution and consensus, separate processes. And we're still iterating on that. Very interesting, let's say, lessons for us, because we don't come from Ethereum background, so it's been super, super cool to learn everything there. I'll go a bit more into the multi-proposer, as I promised. So it is standard in BFT consensus to have the single proposal API. And this is for many reasons, because it's very difficult to do it otherwise. But in this model, there is also, as Brandon was, and before that was also explained by Michael in his talk, there's generally round robin. Sometimes the proposer is selected round robin, but also weighted by stake. That's how it's mostly done in most protocols. And that's the single proposer API. This guy, the proposer, he has pretty much monopoly over what goes into a block. He just goes into his mempool and selects whatever they believe to be the most appropriate to go into that block, sometimes biased, sometimes with MEV and so on. There's obviously problems with it and so on, but it's a very difficult problem to solve, in fact. The multiproposer API changes a bit things in the sense that each API at the application developer that the application developer has is symmetric. So now there is no longer a dedicated proposer, but any validator, as long as you have stake, gets to be able to propose a part of the block, a part that will become a block in every height. So instead of this asymmetric API, propose and sit and wait, you have propose for everyone. Actually, this was our original motivation for working on the multiproposer, is because we saw a lot of, let's say, foot guns in how developers were trying to use either vote extensions with Monad BFT, or they were not using properly the prepare proposal and process proposal. For those of you familiar with Comet, it wasn't very, let's say, easy or ergonomic API. So our original motivation was that. We eventually realized, OK, this has throughput improvements. It has better anti-censorship resistance as well. And basically, in this example, on your right, we have each validators proposing X, Y, Z, and so on. And a block is not shown very clearly in this picture. A block is constructed out of a subset of these proposals. So there's no guarantee that all of these proposals will go in, because you do not have synchrony guarantees in the distributed network. But you can guarantee that a subset of them, and to be more precise, 2f+1 out of 3f+1 in the standard model will go. So out of the 4 block parts that were proposed, 3 of them will go into a block. And in this case, X, Y, and Z. The way we did it, Tendermint, we use it as a black box. We didn't want to change anything inside the consensus state machine, and we put a layer on top of it that we call the multiproposer construction, or Muppet. This is my last slide, basically. How many people in the audience are familiar with the 3 phases of Tendermint? OK, there's a few. So what I'm showing here is 2 heights, or 2 blocks being proposed and just decided, basically. I have height h up until the pre-commit, and then we have 3 phases for height h+1. So we're only seeing the end of height h, and then we're seeing the full phases of height h+1. And what we're seeing horizontally is 4 nodes, each of them labeled with multiproposer. And we see a line in the middle that is, if you will, something like just the representation of the Tendermint algorithm implemented in Malikite. So think of that as like an oracle that represents everything that happens with Tendermint. And we see in the pre-commit stage, we see 4 pre-commits going in. Now, these are pre-commits from the terminology of Tendermint, but these are actually proposals in the terminology of Muppet. So I'm twisting a bit your brain here, but the right name in Malikite terminology, those are proposals. And each of those are signed blocks or block parts, and we're basically overloading the meaning of what pre-commit means in Tendermint. And the rest is pretty straightforward, because the proposer at the height h+1, we are forcing it to construct a block out of at least 2f out of those 3f+1 parts. And then we run the usual Tendermint consensus algorithm, proposal, pre-vote, pre-commit, and the decision is a block constructed out of those. Yeah, I know it's very looks simplistic, but this is it. I'm happy to go into into the questions. Thanks.
We are running a bit short on time, and I want the people that hacked to show what they hacked. So Adi, thank you so much for the talk. And if people want to ask Adi, you can find him. We have plenty of time afterwards.
Thanks, everyone.
Nice. OK, so we made it. Congrats. Bravo. Like, big clap for everyone. So here's what's going to happen now. I'm going to start calling names from the Telegram group, starting with Zach. Zach, please come to the podium. We have USB-C cables for everyone's laptops, not HDMI. if you have a demo, do the demo, and then go on to the next. The demo is like worth 1,000 presentations. Like, don't worry about the slides. Do the demo. If you don't have a demo, do the slides. You have 2 minutes per presentation because we have about 30 people that did things. So yeah, and make sure to plug your laptop like quickly. Don't take your time. Yeah, and the mic is over there. So Zach, you're free to go.
Thanks. Hey, everyone.
he